Our observable universe is immense, yet it may be just a glimpse of what truly exists. What lies beyond the limits of our cosmic vision? Join us as we venture into the unknown, seeking answers to one of science's most profound questions: what exists beyond the edge of the observable universe? Cosmic inflation refers to a rapid expansion of the universe that occurred just after the Big Bang. This theory was proposed to explain several key observations about the universe, including its large-scale uniformity and the distribution of galaxies. During inflation, which lasted for a tiny fraction of a second, the universe expanded exponentially, stretching regions of space far beyond what we can currently observe. This incredibly swift expansion helps to smooth out any irregularities and makes the universe appear nearly homogeneous despite its vastness. The implications of cosmic inflation extend beyond our observable universe. Because inflation likely pushed regions of space outside the reach of our telescopes, there may be vast areas of the universe that we cannot see or detect. These regions could harbor entirely different physical properties, distributions of galaxies, or even different laws of physics. This leads to the thought-provoking concept of a multiverse, where our universe is just one bubble among countless others, each with its unique characteristics. Moreover, inflation theory also suggests that the fluctuations in energy density during this period resulted in the formation of the large-scale structures we see today, such as galaxies and clusters of galaxies. The very seeds of these structures were laid during that brief moment of inflation, guiding how matter gathered under the influence of gravity over billions of years. The concept of regions beyond our observable universe challenges our understanding of reality and invites deeper questions about the nature of the cosmos. If inflation is indeed a true process that occurred, it raises fascinating possibilities about what lies beyond the limits of our sight, tantalizing us with the mystery of the universe's endless expanse. Eternal inflation theory builds upon the idea of cosmic inflation, suggesting that inflationary processes do not just happen once, but can occur repeatedly across different regions of space and time. This leads to the hypothesis that the universe is constantly inflating in certain areas, creating an infinitude of universes, each with its unique conditions and physical laws. In this framework, while some regions of space settle into a stable state and form what we recognize as universes, other regions continue to experience inflation indefinitely. This presents a fascinating picture of the cosmos, where individual universes behave like bubbles in a vast sea of inflating space. Each bubble that forms represents a distinct universe, and within these bubbles, different sets of physical phenomena can unfold. Due to the nature of inflation, some bubbles might lead to universes with different dimensions or entirely altered constants of nature, resulting in a diverse cosmos that stretches infinitesimally beyond our own. One remarkable aspect of this theory is how it reconciles the idea of a singular Big Bang with the diversity we observe in the universe. Rather than a singular event, the bigger picture reveals a multitude of Big Bangs occurring over an endless timeline, spawning numerous universes sampling a vast range of physical realms. This signifies that while we may perceive ourselves as unique inhabitants of one universe, we are part of a broader multiverse scenario where an infinite number of variations exist. Eternal inflation challenges our conventional notions of reality, as it implies that the universe we observe is just a small facet of a far more extensive landscape. In this expansive view, scientific inquiry may uncover an ongoing tapestry woven from an infinite number of cosmic events, each contributing to the rich and enigmatic nature of existence itself. Slow roll and chaotic inflation are two different models of how inflation might occur, each with distinct implications for the concept of a multiverse. The slow roll inflation model describes a gradual extended period of inflation, where a scalar field slowly rolls down its potential energy curve. This scenario leads to a controlled expansion of the universe, resulting in a uniform environment that could allow for regions with varying properties but still share underlying characteristics. It suggests that many parts of the universe can gradually settle into stable states, giving rise to a diversity of outcomes within a relatively predictable framework. In this model, the gradual nature of inflation allows for regions to develop that might evolve into distinct pocket or bubble universes. These bubbles could exhibit different physical properties based on the conditions present in each patch of space. As slow-roll inflation progresses, it can potentially lead to the creation of an array of bubble universes that all stem from a common origin, eventually supporting the idea of a multiverse where each bubble can have varying laws of physics but still retain some observable connections to the vastness of the original inflationary event. Chaotic inflation, on the other hand, arises when one considers the influence of highly energetic fields and initial conditions that are not uniform across the universe. In this model, inflation could arise from a significant divergence in energy levels in different regions of the universe. Consequently, chaotic inflation may produce a far less predictable multiverse, where nearly any initial condition could lead to inflation, giving rise to an extensive range of distinct universes, many of which may behave entirely differently from one another. The varying energy scales could create universes where physical constants differ significantly, possibly giving rise to environments that are inhospitable or dramatically different from our own. The implications of these two different approaches to inflation are profound. Slow-roll inflation hints at a multiverse grounded in a shared set of properties and physical laws, while chaotic inflation suggests a far more heterogeneous multiverse, perhaps full of universes that are drastically different in nature. This variability invites questions about the fundamental nature of reality, challenging our understanding of existence and compelling us to ask what conditions foster the emergence of life in such a boundless cosmos. Bubble nucleation is a crucial concept within inflationary theory that describes how different regions of space undergo a phase transition during the inflationary expansion. As inflation drives a rapid separation of these regions, it can create bubble universes, each with distinct characteristics. When the inflationary field starts to lose energy, it can trigger local events where portions of space transition from the inflationary state to a more stable phase of the universe. This transition is what leads to bubble nucleation. When bubble nucleation occurs, a bubble forms in a specific region of space and expands rapidly. Inside this bubble, the laws of physics may differ from those outside of it, leading to a universe that follows its own set of physical laws and constants. Each time a bubble forms, it can create entirely new conditions and environments as it evolves following the phase transition, effectively birthing a new universe. Thus, through this process, the inflating expanse of cosmic space can lead to the emergence of a vast number of separate bubble universes. Furthermore, bubble nucleation could happen multiple times and in various locations, which means that countless bubbles can form, each representing different outcomes and physical scenarios. As inflation continues to take place, regions of space pop into existence, with infinite possibilities being realized in each newly formed bubble. This suggests that what we perceive as our universe may merely be one of many, nestled within a broader multiverse structure where an infinite array of distinct bubbles coexist, each with unique properties. The concept of bubble nucleation not only enriches the narrative of how our universe might have come into being, but also opens up discussions about the nature of reality itself. It implies that the very fabric of the cosmos is filled with potential universes, each developing from the same fundamental principles, yet diverging into an astounding variety only limited by the initial conditions of inflation. In inflationary cosmology, the concept of pocket universes refers to distinct regions of spacetime that form during the inflationary phase. As inflation progresses, various patches of the inflating universe can stop inflating at different times due to fluctuations in the energy field responsible for inflation. When a specific region ceases to inflate, it transitions into what is termed a pocket universe. This is analogous to bubbles forming in boiling water, where each bubble represents a self-contained universe that can evolve independently. Pocket universes arise from the dynamics of the inflaton field, which drives inflation. When a region of space reaches a state where the inflaton field reduces its energy, that particular area stops inflating and dilates into a universe with its own properties and physical laws. Meanwhile, surrounding regions continue to experience inflation, meaning they remain in a state of rapid expansion. This process creates a scenario in which numerous pocket universes can exist within the same overarching inflationary space, each with potentially different physical constants or dimensions. The formation of pocket universes contributes to the idea of a multiverse. Each pocket universe can develop independently, leading to a diverse assortment of conditions and physical phenomena distinct from those in neighboring pocket universes. Some may be similar to our own, while others could possess radically different characteristics that may not support life as we know it. This structure presents fascinating implications for our understanding of the cosmos. The presence of pocket universes suggests that the universe is not just one homogeneous entity, but rather a complex, interconnected web of separate universes, all arising from the same foundational inflationary event. It prompts deeper questions about what defines a universe and challenges our perceptions of reality by hinting at an infinite variety of cosmic possibilities waiting to be explored. Inflation addresses critical issues in cosmology known as the horizon problem and the flatness problem, which challenge our understanding of the universe's structure and behavior. The horizon problem arises from the observation that regions of the universe that are far apart have nearly identical temperatures and properties despite being separated by vast distances. Without inflation, it is difficult to explain how these regions could have exchanged information or energy, given that light has not had enough time to travel between them since the Big Bang. Inflation provides a solution by proposing that during the very early moments of the universe, a rapid expansion pushed these regions together. This extreme growth took place before the speed of light barrier prevented them from communicating. As a result, areas that were once in close proximity underwent inflation and later became vastly separated while retaining similar characteristics. This explanation allows for the uniformity observed in the cosmic microwave background radiation, as it posits that the observable universe was homogeneously smoothed out through this rapid expansion. The flatness problem relates to the critical density of the universe, explaining why our universe appears nearly flat rather than curved. Theoretical models predict that any tiny deviation from this critical density would grow over time, leading to either an open or closed universe. However, we observe that the universe's geometry is close to flat, which seems improbable given the long timeline since the Big Bang. Inflation resolves this by suggesting that the explosive expansion stretches any initial curvature to a point where the universe behaves as if it is perfectly flat, effectively diluting any spatial curvature that may have been present earlier. These solutions carry intriguing implications for the nature of space beyond our observable universe. If inflation continually creates regions of space where inflation is still occurring, it suggests that the universe might be vast and ongoing, potentially leading to additional bubble and pocket universes that exist outside our observational limits. This means there could be a seemingly infinite expansion of regions with varying properties just beyond our reach, fostering a deeper understanding of the multiverse concept and reshaping our fundamental perspective on the cosmos. The theory of false vacuum decay centers on the idea that the universe could be in a metastable state known as a false vacuum. In this context, a vacuum refers to a state of minimal energy, but a false vacuum is not the absolute lowest energy state that the universe could reach. Instead, it is a local minimum where the conditions appear stable but can potentially decay, leading the universe to transition to a lower energy true vacuum state. This process can give rise to dramatic changes in the fabric of space-time, including the creation of new universes. When a false vacuum decays, the transition might happen through quantum tunneling, which allows the system to escape from the false vacuum state and shift into a true vacuum state. This event is localized and can spawn a bubble of true vacuum that expands at a rapid pace, similar to other scenarios discussed in inflationary cosmology. The region where this decay occurs transforms dramatically, resulting in an entirely new universe emerging from the decay process. As this bubble of true vacuum expands, it can lead to the formation of a new universe with distinct physical properties, different constants, and potentially unique laws of physics. In this way, false vacuum decay can be viewed as a mechanism by which the cosmos might not only generate new worlds, but an entire multiverse. Each bubble created through this decay could follow a different evolutionary path, leading to varied outcomes and diverse cosmic environments. The implications of false vacuum decay stretch beyond just new universe formation. Some theorists suggest that our own universe could be experiencing this state of decay, which raises intriguing questions about the future and stability of our cosmos. It fuels discussions about the nature of reality and the processes that foster the birth of entirely new realms of existence, emphasizing the ever-expanding mystery of the multiverse surrounding us. The inflationary multiverse is a specific framework within the broader concept of the multiverse that arises from the principles of cosmic inflation. It differs significantly from other multiverse theories, particularly in its foundation, mechanisms, and implications regarding the nature of parallel universes. In the inflationary multiverse, the creation of different universes or bubbles stems from fluctuations in the inflationary field, leading to isolated pocket universes with potentially varying physical laws and constants. One of the key distinctions is how the inflationary multiverse emerges from the rapid expansion process. Inflation suggests that different regions of space can stop inflating at different times, creating numerous bubble universes, each emerging from a common inflationary state. These bubbles can possess unique properties, leading to a vast landscape of universes that vary in structure, behavior, and even fundamental constants. This contrasts with other multiverse models, such as the quantum multiverse, which arises from interpretations of quantum mechanics, suggesting an infinite number of branching realities based on every quantum decision or possibility. Another difference lies in how the inflationary multiverse addresses the fine-tuning problem in cosmology. While many multiverse theories propose that our universe is just one of an infinite series of random outcomes, the inflationary multiverse frames this diversity as a consequence of inflationary processes. By supporting the idea of pocket universes, inflation guides the notion that specific regions could develop tailored properties based on their initial conditions. In contrast, other multiverse models may lack a mechanism to explain the emergence and structure of those alternate realities. Additionally, while some multiverse theories propose varying dimensions or different laws of physics based on abstract concepts like string theory or cosmological models, the inflationary multiverse is grounded in observations like the cosmic microwave background radiation. This observational basis provides a more scientific footing, highlighting how inflation leads to observable phenomena. Overall, the inflationary multiverse frames a rich tapestry of possible realities, while remaining tightly woven with the principles of cosmic inflation and the observed universe. Support for the theory of cosmic inflation extending beyond our observable universe largely hinges on a few key observational phenomena, notably the uniformity and structure of the cosmic microwave background radiation, as well as gravitational wave signatures. The cosmic microwave background radiation is a remnant from the early universe that fills the cosmos and provides a snapshot of our infant universe just after the Big Bang. Observations from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have revealed remarkable uniformity in temperature across large swathes of the sky. This uniformity is puzzling because regions of the universe that are far apart should not have been able to exchange information or energy since they were never in contact before inflation. Cosmic inflation theorizes that the rapid expansion stretched these regions, allowing them to form homogeneously before becoming causally disconnected. Such explanations lead to the tantalizing idea that inflation extended beyond our observable bounds, influencing regions we cannot see. Another piece of observational evidence comes from the patterns or fluctuations in the cosmic microwave background radiation. The slight temperature variations mapped by these satellites indicate density fluctuations that eventually evolved into galaxies and large-scale structures. Inflation theory explains these fluctuations as quantum perturbations that were magnified during the inflationary phase, suggesting that similar processes could occur in regions beyond our current horizon. If true, this would imply that the universe is far larger than what we can observe, extending into regions where inflation may still influence ongoing cosmic development. Gravitational waves, generated by violent cosmic events such as the merging of black holes or neutron stars, present another potential avenue for supporting the idea of an infinitely expanding inflating universe. Future observations from detectors like LIGO and Virgo may uncover gravitational waves that originated from earlier inflationary processes. In particular, the existence of a unique spectrum of gravitational waves resulting from inflaton interactions could hint at inflation's lasting impacts beyond our visible universe, laying the groundwork for unraveling the cosmos's far-reaching mysteries. The observational evidence supporting cosmic inflation suggests that the influences of such an early rapid expansion extend beyond our observable universe, inviting compelling questions about the nature of reality and the potentially infinite cosmos that awaits exploration. Eternal inflation introduces the notion of a fractal-like structure in the multiverse by proposing that inflationary processes do not occur uniformly or simultaneously across all regions of space. Instead, some areas can continue to inflate indefinitely, while others settle down into stable bubble universes. This leads to a scenario where inflation is an ongoing phenomenon, perpetually giving rise to new regions of space undergoing their own inflationary events. As inflation perpetuates in specific pockets of the universe, it creates a hierarchical landscape resembling a fractal. In a fractal structure, patterns repeat at varying scales, and similarly, in this multiverse scenario, each bubble universe can itself contain smaller regions that might also undergo inflation. Many of these smaller regions might continue inflating, potentially leading to further bubble formations within them. The end result is a complex self-similar arrangement of universes nested within one another, where larger structures encompass an infinite variety of smaller evolving subregions. The fractal-like characteristics arise from the dynamics of eternal inflation. For example, while some bubble universes stabilize into regions where life and galaxies can form, others remain in an inflationary state, constantly producing new bubbles. This diversity means that as one examines these cosmic bubbles, one may find structures that mimic the organization and variety found in fractals, where smaller details reflect larger patterns. Similarly, just as one can zoom into a fractal and uncover intricate designs, the multiverse invites concepts of infinity and endless variation at any scale. This self-similar structure inherent to eternal inflation presents not only an elegant model for understanding the multiverse, but also emphasizes its complexity. It challenges us to consider the richness of reality beyond our observable universe and how myriad forms of existence could be interconnected through ongoing processes governed by the same fundamental dynamics of inflation. Ultimately, this fractal-like view of the multiverse invites exploration into the infinite possibilities that lie beyond our current comprehension of space and time. String theory suggests the existence of multiple universes through its fundamental premise that the building blocks of all matter and forces are not point-like particles, but rather tiny, vibrating strings. These strings can exist in different vibrational modes, and their different patterns of vibration correspond to the various particles and forces we observe in our universe. Because string theory allows for multiple dimensions beyond the familiar three of space and one of time, it opens up the possibility of diverse realities existing simultaneously. One of the intriguing aspects of string theory is its multiple solutions, particularly regarding the shapes and sizes of extra dimensions. The theory predicts that additional dimensions beyond the observable four can be compactified or curled up in complex ways, resulting in a vast landscape of possible configurations. This leads to the idea of a landscape multiverse, where each unique configuration of dimensions corresponds to a distinct universe with its own set of physical laws and constants. As a result, the universe we inhabit is just one of many that could emerge from this landscape of possibilities. Furthermore, string theory accommodates various mechanisms for universe creation, including those similar to cosmic inflation. For instance, certain scenarios within string theory might suggest that different regions of space could undergo inflation differently, generating a multitude of pocket or bubble universes with varying properties. Each of these universes might exhibit its own unique physical characteristics based on the particular vibrational states of strings and the compactification of its extra dimensions. The implications of string theory extend beyond the mere existence of multiple universes. They also provoke questions about the nature of reality itself. If string theory holds true, our universe could be just one small part of a much larger and intricate multiverse, challenging our traditional notions of singular existence. Ultimately, the framework of string theory offers a rich tapestry of mathematical possibilities, paving the way for a deeper understanding of how these multiple universes could interact and influence one another within a grand cosmic architecture. The concept of the string theory landscape refers to the vast array of possible solutions that arise from string theory, particularly concerning the configurations of extra dimensions and the vibrational modes of strings. In string theory, while the fundamental nature of matter is represented by one-dimensional strings, the arrangement of additional spatial dimensions can lead to an immense number of possible outcomes for the physical laws of different universes. This landscape is not just a mere abstract notion, but a comprehensive framework that suggests each unique solution corresponds to a distinct universe, leading to the idea of a multiverse. The landscape emerges from the process of compactification, where extra dimensions beyond our familiar four are curled up in intricate ways. These configurations can vary widely, resulting in different effective physical constants between each universe. String theory allows for an astronomical number of ways to compactify these extra dimensions, leading to a spectrum of possible laws of physics. As some configurations are conducive to forming a universe like ours, others could produce entirely different laws and constants, effectively creating a myriad of universes, each with its own characteristic behaviors. Moreover, the string theory landscape underscores the concept of vacuum states and their stability. In this framework, each vacuum state can correspond to a particular universe, governed by specific physical laws and constants. These vacua can have varying energies, and transitions between different vacua may lead to the formation of new universes. This process can resemble the idea of eternal inflation, where certain regions of the landscape undergo inflation while others settle down, producing a plethora of bubble universes along the way. The implications of the string theory landscape extend far beyond mere existence. They challenge our understanding of reality. If the landscape captures a vast array of universes, it accounts for the fundamental question of why our universe appears so finely tuned for life. The multitude of configurations suggests that we reside in a particular stable vacuum simply because it happens to support the conditions conducive to our existence, while many other vacua may lead to entirely different and possibly inhospitable realities. This richness in potential universes ultimately invites intriguing questions about the nature of existence, the mechanisms that govern reality, and the underlying connections between different universes in the expansive multiverse landscape. In string theory, extra dimensions play a vital role in the framework that allows for the existence of multiple universes. While our everyday experience is confined to 3 dimensions of space and 1 of time, string theory posits additional spatial dimensions that are typically compactified or hidden from our direct perception. These extra dimensions can influence the physical properties of particles and forces, and they provide the potential for entirely separate, distinct universes to emerge within the same theoretical framework. One way extra dimensions might harbor other universes is through the concept of compactification. In string theory, there can be multiple ways to compactify these dimensions, with various shapes and sizes leading to different physical properties. Each compactification scheme can correspond to a different universe with its own set of physical laws, constants, and particle interactions. For example, one arrangement of the extra dimensions might lead to a universe very similar to ours, while another configuration might produce dramatically different physical laws, resulting in a diverse array of universes existing side by side. Additionally, these extra dimensions can act as conduits or pathways for different vacuum states. The landscape of string theory indicates the existence of many possible vacuum states, each representing a distinct configuration of energy and particle physics. Some regions of these extra dimensions could stabilize into separate vacua, each evolving into its own universe. These vacua may interact through various processes, potentially enabling transitions between states or the birth of new universes from existing ones through phenomena analogous to bubble nucleation. Moreover, the extra dimensions could allow for universes to be entirely disconnected from one another while still originating from the same fundamental string theoretic principles. Essentially, different configurations of extra dimensions could lead to regions of space that evolve independently, with their physical characteristics shaped by the specific dimensional geometry. This setup fosters a rich multiverse structure, where myriad universes can coexist, potentially harboring a vast range of fundamental interactions that might allow for life, or perhaps none at all. The concept of extra dimensions in string theory not only enriches our understanding of how multiple universes might exist, but also opens doors to contemplate the interplay of varying physical laws across these realms. Each extra-dimensional configuration could yield unique realities, posing profound questions about the nature of existence itself and the underlying architecture of everything we observe. Brain cosmology is a fascinating concept within string theory that expands our understanding of the universe by introducing the idea of multi-dimensional objects known as brains. In this framework, Our observable universe can be envisioned as a three-dimensional brain embedded within a higher dimensional space, often referred to as the bulk. These brains can have varying dimensions, with our own universe being a three-dimensional brain living within a higher dimensional bulk that contains additional brains and dimensions. In brain cosmology, the interaction between different brains can lead to the creation of parallel universes. When two brains approach each other in the bulk, their interaction can produce gravitational effects and give rise to phenomena such as the Big Bang. This suggests that the universe we inhabit is not isolated. Rather, it could be one of many brains in this higher dimensional space. Each of these brains can host its own universe, potentially with different physical laws and constants. Consequently, when interacting, the brains could lead to the formation of new universes through mechanisms akin to collisions, which could create a hot, dense state similar to the conditions at the genesis of our own universe. Moreover, the characteristics of each parallel universe are determined by the specific properties of the brain on which they reside. This can include variations in the number of dimensions, the types of forces in play, and the underlying structures of matter. As a result, brain cosmology envisions a multiverse filled with different brains, each supporting a unique universe. Some might have laws of physics that are close to ours, while others could behave in fundamentally different ways, further enhancing the diversity of potential realities. The implications of brain cosmology extend beyond the mere existence of parallel universes. It challenges our traditional notions of space and time, suggesting that the interactions and dynamics of these higher dimensional brains could influence the evolution and behavior of the observable universe. This perspective invites a myriad of questions regarding the nature of reality, the origins of our universe, and the underlying connections between multiple universes inhabiting a complex, multidimensional landscape. Ultimately, brain cosmology lays the groundwork for an intricate web of universes existing together in a grander, higher dimensional framework, each contributing its unique thread to the fabric of existence. M-theory emerges as a groundbreaking framework in theoretical physics that aims to unify the 5 distinct string theories that have been developed over the years. Each of these string theories describes fundamental particles as one-dimensional strings, but they differ in the number of dimensions they occupy and the specific types of strings they include. M-theory introduces an 11th dimension, which is key to connecting these various string theories. By doing so, it suggests that all of these theories are simply different manifestations of the same underlying principles, with M-theory serving as a unifying structure that encapsulates them all. A significant implication of M-theory lies in its capacity to describe higher dimensional objects known as brains, which can have various dimensionalities. For instance, while strings are one-dimensional objects, brains can exist as two-dimensional surfaces or even higher dimensions. This added complexity leads to a more expansive understanding of the universe, allowing for the exploration of phenomena previously beyond the scope of traditional string theories. The 11th dimension provides this framework's versatility and richness, suggesting a more interconnected and intricate structure of space-time than previously conceived. The implications of M-theory extend beyond just unifying string theories. They also prompt intriguing possibilities regarding the multiverse. In this context, the multiverse refers to the idea that our universe might be just one of many, each with distinct physical laws and constants. M-theory's additional dimensions and brain interactions imply a landscape where countless universes can emerge, each with its unique configuration of strings and brains. This opens up possibilities for different versions of reality shaped by the initial conditions and topological properties of these higher dimensional constructs. As researchers delve deeper into M-theory, they uncover potential connections with cosmological phenomena such as cosmic inflation and the very nature of black holes. The implications of this theory extend far into our understanding of time, space, and the fundamental fabric of reality itself. What was once considered abstract speculation in theoretical physics is beginning to gain traction, pulling together various ideas and offering a tantalizing glimpse into the complexity of the cosmos, where the idea of a multiverse is not merely conjectural, but a fundamental aspect of a more comprehensive physical theory. The ekpyrotic model presents an alternative perspective on the origins of our universe, positing that it emerged from the collision of two three-dimensional brains in a higher dimensional space. This collision occurs within a framework of extra dimensions, which are integral to the model's underlying mechanics. Unlike the conventional Big Bang theory, which suggests a singular explosive event from an infinitely dense point, the ekpyrotic scenario involves two brains that exist in a multidimensional space, potentially sharing properties with theories like M-theory. In this model, the brains represent separate universes, and when they collide, the friction and energy generated during this event can produce a hot, dense state, akin to the conditions described in traditional Big Bang cosmology. This collision leads to the formation of a new universe, sparking processes similar to those observed in cosmic inflation. The advantage of using extra dimensions is that they allow this brain interaction to occur in a way that can account for various observed cosmological phenomena while maintaining coherence with the principles of modern physics. Furthermore, the extra dimensions in the ekpyrotic model play a crucial role in resolving certain challenges faced by the conventional Big Bang theory, such as the homogeneity and isotropy of the universe. By allowing for a more complex structure beyond the traditional three spatial dimensions, the model can account for a wide range of initial conditions and their respective outcomes. The interaction of brains helps to explain the uniform distribution of matter and energy across the cosmos, as well as the potential for variations in cosmic microwave background radiation. This model also invites consideration of the multiverse concept. If our universe results from a collision between brains, it raises the possibility that other brains exist, leading to the birth of multiple universes, each with different physical properties and laws. By exploring these extra-dimensional interactions, the ekpyrotic model offers a fascinating and innovative take on how our universe might have originated, significantly broadening the discussion surrounding cosmic beginnings and the nature of reality itself. Collisions between brains are pivotal in the ekpyrotic model of cosmology, suggesting a fascinating mechanism for the creation of new universes. In this framework, our universe is conceptualized as one of many that exist on three-dimensional brains embedded within a higher dimensional space. These brains can represent distinct universes, and their movement through this higher dimensional landscape can lead to interactions that have profound consequences. When two brains collide, the energy released during the collision can compress the fabric of space-time, creating a state of extreme density and temperature. This interaction can trigger a series of dynamic processes that resemble the conditions described in the traditional Big Bang cosmology. The energy from the collision may result in the generation of particles and radiation, effectively creating a new cosmos that expands and evolves from this incredibly hot and dense state. The specifics of this creation process involve complex physics. As the brains interact, gravitational and electromagnetic forces can come into play, influencing how matter emerges and evolves in the newly formed universe. The resulting expansion can lead to a rapid inflationary phase, smoothing out any irregularities and establishing a uniform structure throughout the young universe. This expansion can account for various observed phenomena, including the vastness of the cosmos and the uniform distribution of cosmic microwave background radiation. Moreover, if the brains continuously move within this higher dimensional space, every collision can potentially birth new universes. Each one may inherit different physical properties based on the conditions prevailing during its specific brain collision. This cyclical process hints at a multiverse scenario, where a multitude of universes are formed, each with its distinct characteristics, contributing to the larger tapestry of reality. The idea that our universe could be the result of such collisions encourages a deeper inquiry into the nature of existence itself and the unseen dimensions that may underpin all we observe. The holographic principle is a captivating concept in theoretical physics that suggests all the information contained within a volume of space can be encoded on its boundary, much like a hologram. This idea challenges our traditional understanding of dimensions and reality. Instead of viewing our three-dimensional universe as the full picture, the holographic principle posits that the fundamental descriptions of physical phenomena can be represented by information stored on a two-dimensional surface. This principle finds its roots in black hole thermodynamics, where researchers discovered that the entropy of a black hole, which is a measure of its information content, is proportional to the area of its event horizon rather than its volume. The implications of the holographic principle extend well beyond black holes. This principle suggests that the universe's underlying fabric is far more intertwined than previously considered. It indicates that the laws of physics, space, and time may not be as straightforward as they seem. In a holographic universe, three-dimensional experiences would simply be projections of more fundamental, two-dimensional information. This radical shift in how we perceive dimensionality opens new avenues for understanding the relationships between gravity, quantum mechanics, and thermodynamics. When we contemplate universes beyond our own, the holographic principle suggests that distinct universes might be represented by different configurations of information on various two-dimensional surfaces. In this perspective, each universe could exist as a holographic projection, arising from its unique boundary data defined in the extra dimensions. This echoes the multiverse concept, where an infinite variety of realities could emerge based on different underlying physical information and laws. Furthermore, the holographic principle points toward a potential unification of quantum mechanics and gravity, hinting at a more profound connection between our universe and others that may exist in this framework. As scientists explore these ideas through the lens of string theory and other approaches, the implications of the holographic principle may provide insights into the very nature of existence itself, including the fundamental structures of space-time and the possibility of multiple, interrelated universes within a vast cosmic landscape. In string theory, the concept of compactified dimensions is a crucial component that contributes to our understanding of the universe and its potential connections to other universes. String theory proposes that the fundamental building blocks of matter are not point-like particles, but rather one-dimensional strings that vibrate at different frequencies. For these strings to behave as observed in our three-dimensional world, additional spatial dimensions are required, and some of these dimensions may be compactified. Compactification refers to the process in which extra dimensions are curled up or folded into tiny, unobservable shapes, often at scales far below the level of current experimental detection. While our familiar universe has three spatial dimensions, theories such as string theory posit that there could be 6 or more additional dimensions. These compactified dimensions can take on various geometries, influencing the properties of the strings and, consequently, the types of particles and forces that appear in our observable universe. The unique arrangement of these compactified dimensions plays a significant role in shaping not only the characteristics of our universe, but also the potential existence of other universes. Each specific compactification can give rise to a different physical scenario, with its unique set of fundamental constants and laws. This means that different configurations of the compact dimensions could lead to entirely distinct universes, each with different properties, leading to the concept of a multiverse where numerous universes coexist, shaped by the varied geometrical arrangements of their compact dimensions. As scientists explore the implications of compactified dimensions, they encounter the fascinating prospect that our universe might just be one of many emerging from a higher dimensional framework. With each arrangement of the compactified dimensions producing a unique universe with varying physical rules, the relationship between these distinct realities becomes a key area of investigation. Underlying this scenario is the potential interplay between string theories and the broader landscape of cosmology, offering insights into the very nature of existence and the multitude of universes that could lie beyond the one we inhabit. The existence of extra dimensions, a fundamental aspect of string theory and various other theories in physics, remains a topic of great interest and exploration. While direct observational evidence for these dimensions is elusive, several avenues of research and experimental strategies might provide indirect support for their existence. One promising area for detecting extra dimensions comes from studying the behavior of gravity at very small scales. According to some theoretical models, if extra dimensions exist, gravity could behave differently than it does in our familiar three-dimensional space, particularly at scales smaller than those we currently probe. Experiments designed to test the inverse square law of gravity at tiny distances may reveal deviations predicted by theories that incorporate extra dimensions. If gravity were to weaken more rapidly than expected, this could indicate the influence of dimensions beyond our perception. Another significant avenue lies in the realm of high-energy particle physics, particularly in experiments conducted at particle accelerators like the Large Hadron Collider. In certain models, such as those inspired by string theory, collisions at high energies could produce particles that can escape into extra dimensions, resulting in missing energy and momentum in particle collision outcomes. This could provide an intriguing signature in the data collected from high-energy interactions. The presence of these dimensions might also lead to the production of specific particles, such as Kaluza-Klein modes, which are manifestations of higher dimensional physics. Cosmic phenomena might also serve as a window into the existence of extra dimensions. For example, the behavior of cosmic rays traveling through space at ultra-high energies may be influenced by unseen dimensions. Additionally, gravitational waves, ripples in space-time produced by massive objects, could reveal insights about the structure of space-time itself. If extra dimensions exist, they may affect gravitational wave propagation and could offer clues about their dimensionality. Lastly, observations related to cosmic inflation, the rapid expansion of the universe after the Big Bang, hint at scenarios influenced by higher dimensional physics. Some inflationary models incorporate extra dimensions, and analyzing the cosmic microwave background radiation for specific signatures might provide further evidence supporting the existence of these hidden dimensions. These multifaceted approaches reflect the ongoing quest to unravel the mysteries of the universe and our place within it, with the potential discovery of extra dimensions holding transformative implications for our understanding of reality. The many worlds interpretation of quantum mechanics is a fascinating and controversial perspective that seeks to resolve the peculiarities of quantum behavior through the concept of branching universes. At its core, this interpretation suggests that every time a quantum event occurs with multiple possible outcomes, the universe splits into distinct branches, each of which realizes one of those outcomes. Rather than collapsing into a single reality upon measurement, as in the traditional Copenhagen interpretation, the quantum system continues to exist in a superposition of states. Every possible outcome happens, but in separate, non-communicating branches of the universe. This idea arises from the mathematical framework of quantum mechanics, which describes particles as being in multiple states simultaneously until they are observed. The many worlds interpretation posits that the act of observation does not cause the wave function to collapse into one state, but instead leads to the creation of multiple coexisting realities where all possible outcomes occur. As a result, each observer perceives only one outcome, while all other possibilities exist in parallel universes. One implication of the many worlds interpretation is the notion of an infinitely branching multiverse, where an enormous number of universes can exist concurrently, each reflecting different outcomes of every quantum event. This leads to profound philosophical questions regarding reality, identity, and the nature of existence. If every choice or chance event creates a separate universe, it raises intriguing possibilities about the lives and decisions of individuals across these multiple realities. While the many worlds interpretation provides a consistent framework for understanding quantum phenomena, It does not offer empirical predictions that can be experimentally tested, which is a common criticism. Despite this, it has gained traction among some physicists and cosmologists for its elegant approach to addressing the foundational problems of quantum mechanics. As research continues to explore these dimensions of reality, the many worlds interpretation remains a compelling lens through which to consider the complexities of the universe and the fundamental nature of existence itself. Quantum decoherence plays a significant role in explaining the many worlds interpretation of quantum mechanics and how it relates to the concept of parallel universes. At its core, decoherence describes the process by which a quantum system loses its quantum behavior, specifically its ability to exist in a superposition of states due to interactions with its environment. When a quantum system interacts with many particles in the environment, this interaction effectively causes the different branches of a superposition to become entangled with the states of these external systems. As a result, the coherent superposition becomes fragmented into distinct outcomes that are no longer able to interfere with one another. In the context of the many worlds interpretation, decoherence helps to clarify how different outcomes of a quantum event can exist simultaneously without interfering with each other. When a quantum event occurs, such as a particle being in two places at once, decoherence ensures that the possible outcomes of this event become effectively independent from each other. Once decoherence has taken place, the universe branches into separate realities, each corresponding to a different outcome. Thus, while the original quantum superposition captured all possibilities, decoherence causes them to manifest as distinct, parallel universes that do not interact with each other. This concept provides a powerful framework for understanding why observers in one universe only experience a single outcome of a quantum measurement. As the environment interacts with the quantum system, the coherence necessary for observing superpositions is lost, leading to the relative independence of the various branching universes. Each branch is consistent with its own recorded history, devoid of interference from the others. Furthermore, quantum decoherence also helps to address the classical behavior exhibited by macroscopic objects. In classical mechanics, reality appears deterministic and unambiguous, while quantum mechanics introduces uncertainty and superpositions. Decoherence bridges this gap by explaining why macroscopic objects behave as classical entities despite being composed of quantum particles. The rapid interactions and entanglements with their environments facilitate the emergence of classical-like states, leading to the apparent definiteness observed in everyday life. Quantum decoherence not only delineates how superpositions evolve into distinct outcomes, but also underpins the many worlds interpretation by allowing for the existence of parallel universes. Each of these branches reflects a different realization of quantum possibilities, reinforcing the richness and complexity of reality as described by modern physics. Quantum tunneling is a fundamental phenomenon in quantum mechanics that describes the ability of particles to pass through potential energy barriers, even when classical physics suggests they do not have enough energy to do so. In classical terms, if a particle lacks the necessary energy to cross a barrier, it will simply bounce back. However, in the quantum realm, particles are described by wave functions that embody probabilities, rather than certainties. This means that there is a finite probability that a particle can exist on the other side of a barrier, effectively tunneling through it. The mechanism behind quantum tunneling involves the wave-like nature of particles and the principles of quantum superposition. When a particle encounters a barrier, its wave function does not abruptly stop at the barrier. Instead, it extends into and beyond the barrier. Although the likelihood of finding the particle on the other side diminishes with increased barrier height or thickness, there remains a non-zero probability for the particle to tunnel through it. This phenomenon has practical implications in various fields, including nuclear fusion, where it helps explain how protons can overcome the electromagnetic repulsion of each other within stars. When considering the creation of new universes, quantum tunneling can be theorized as a mechanism that allows for transitions between different states of the cosmos. In certain scenarios, such as the concept of a false vacuum in cosmology, a particular region of space may be in a metastable state that captures energy and fails to reach a lower energy state, the true vacuum. Quantum tunneling provides a pathway for this metastable vacuum to transition into a true vacuum, which can trigger inflationary expansion. Such a transition can cause a localized region of space to rapidly expand, leading to the formation of a new universe. This tunneling process can be understood within the framework of the multiverse hypothesis. If our universe is indeed part of a much larger landscape of possible configurations, quantum tunneling might facilitate the birth of new, independent universes, each with different physical constants and properties. Each tunneling event could lead to the production of diverging branches of reality, giving rise to a multitude of distinct universes, each shaped by unique circumstances and outcomes. Thus, quantum tunneling serves as not only a captivating physical insight into particle behavior, but also a conceptual tool that may help explain the creation of new universes within the broader context of cosmological theories. This interplay between quantum mechanics and cosmology offers profound implications for our understanding of existence, reality, and the vastness of the cosmos. The Copenhagen interpretation and the many worlds interpretation offer fundamentally different views of reality that stem from their distinct approaches to the nature of quantum mechanics. The Copenhagen interpretation, widely regarded as one of the earliest and most traditional interpretations, posits that quantum systems do not have definite properties until they are measured or observed. According to this view, particles exist in a state of superposition, where they can be in multiple states simultaneously. It is only upon measurement that the wave function collapses, and the system resolves into one specific outcome, which is what the observer perceives. In contrast, the many worlds interpretation fundamentally challenges the notion of wave function collapse. It suggests that rather than collapsing into a single outcome upon observation, every possible outcome of a quantum event actually occurs, but in separate, non-communicating branches of the universe. Each possible state is realized in a distinct universe, meaning that all outcomes coexist simultaneously in a vast multiverse. The many worlds interpretation removes the need for an observer to cause the collapse of the wave function, thus maintaining the coherent evolution of quantum systems even during measurement. This core difference leads to distinct implications for understanding reality. The Copenhagen interpretation implies a certain randomness inherent in quantum mechanics, as the act of observation determines which outcome will be realized. There is an element of unpredictability and a separation between the observer and the observed, raising questions about the role of consciousness and measurement in shaping reality. In this framework, only one universe exists at any given moment, defined by the outcomes of measurements performed by observers. On the other hand, the many worlds interpretation presents a more deterministic view of reality, where all outcomes unfold in a branching multiverse. No randomness exists at the fundamental level, rather the reality encompasses all possibilities at once. Each observer only experiences one branch, leading to the apparent randomness observed in quantum mechanics, but all other outcomes exist in parallel. This interpretation provides a more unified account of quantum behavior, removing the need for collapse and reconceptualizing the observer's role. The differing perspectives on reality thus reflect deeper philosophical implications about existence, consciousness, and the nature of the universe. While the Copenhagen interpretation emphasizes the significance of measurement in shaping reality, the many worlds interpretation posits a richer and more expansive structure where every possibility is realized, fundamentally altering our understanding of existence and the complexities of the cosmos. Quantum entanglement is a fundamental phenomenon in quantum mechanics, where two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. When two particles are entangled, their properties become linked, meaning that measuring one particle's state provides immediate information about the state of its entangled partner. This connection remains intact even if the particles are light years apart, a feature that Einstein famously referred to as spooky action at a distance. In the context of multiple universes, entanglement can play a significant role in discussions pertinent to the many worlds interpretation of quantum mechanics. In this framework, every quantum event that has multiple potential outcomes leads to the branching of the universe into separate realities, each reflecting a different outcome. When particles are entangled, the measurement of one particle does not collapse the system into a single state. Rather, it reflects the outcome of the entire entangled state across all branches of existence. The intriguing aspect of entanglement in relation to multiple universes is how it illustrates the interconnectedness of different branches. When a measurement occurs in one universe, resulting in a specific outcome, it influences the states of the entangled particles across all other branches simultaneously. Each branch represents a distinct reality where different outcomes are experienced, but the entangled nature of the particles maintains a form of correlation between these universes. This highlights a potential relationship between them, even if they operate independently. Moreover, quantum entanglement raises profound questions about the nature of information and reality across these branching universes. It suggests that all branches might contain overlapping historical information about their entangled states, leading to intriguing implications regarding the foundations of quantum mechanics and the fabric of reality itself. In a sense, entangled particles act as conduits that connect multiple universes through their shared quantum properties, creating a rich tapestry of interrelated realities. Understanding quantum entanglement provides valuable insights into the nature of information, measurement, and the very structure of reality in quantum mechanics, particularly when woven together with concepts of parallel universes. As researchers continue to delve into the mysteries of entanglement, its relationship to the many worlds interpretation, and its broader implications for cosmology, it further emphasizes the interconnectedness of the universe at its most fundamental level. Quantum superposition is a fundamental principle of quantum mechanics that states a quantum system can exist in multiple states simultaneously until it is measured or observed. This means that a particle, for instance, does not have a singular position or momentum, but rather embodies all possible positions and momenta at once, represented mathematically by a wave function. It is only upon measurement that this superposition collapses into a specific state and the observer perceives a definite outcome. The relationship between quantum superposition and the existence of parallel universes becomes particularly striking in the context of the many worlds interpretation of quantum mechanics. According to this interpretation, instead of collapsing into one distinct outcome when measured, the wave function continues to evolve without collapse. Each possible outcome of the measurement results in a branching of the universe, where every possibility coexists in a different branch or world. Therefore, quantum superposition serves as the critical mechanism that gives rise to these multiple realities by retaining all potential states rather than settling on just one. For example, consider a quantum experiment involving a particle that can be in a state of spin-up or spin-down. In superposition, the particle is both spin-up and spin-down at the same time. When a measurement is made, rather than collapsing to just one state, the universe branches into two distinct realities, one where the result of the measurement shows spin-up and another where it shows spin-down. Each of these outcomes represents a separate universe, highlighting how superposition leads to the proliferation of multiple universes based on the different outcomes of quantum events. This interplay between superposition and parallel universes raises compelling questions about the nature of reality and existence. Each branch that emerges from a superposition embodies a different outcome, creating a vast multiverse comprised of countless variations of reality, each evolving from the results of quantum processes. The many worlds interpretation thus weaves quantum superposition into its fabric, suggesting that the entirety of existence consists of a multitude of branching paths stemming from the fundamental principles of quantum mechanics. Ultimately, quantum superposition not only explains a range of quantum phenomena, but also provides a conceptual foundation for understanding the profound implications of parallel universes, encapsulating the complexities of reality in a manner that challenges conventional perspectives on existence, observation, and the universe itself. In quantum mechanics, the role of observation is a pivotal concept that has sparked extensive debate and interpretation. The traditional Copenhagen interpretation suggests that quantum systems exist in a state of superposition, with multiple possible outcomes, until they are observed or measured. Upon measurement, the wave function collapses to reveal a single definite state, and this act of observation effectively determines the reality of the quantum system. This introduces a degree of subjectivity into the nature of reality, raising questions about the observer's role and the implications of consciousness in shaping outcomes. This view implies that reality is not static or absolute, but is influenced by observation. The measurement problem, which centers on how and why wave function collapse occurs, becomes a central focus of quantum mechanics. Philosophical inquiries arise concerning what constitutes an observer. Is it merely a conscious being, or can any interaction with the environment suffice to cause a collapse? This brings forth complex discussions about the nature of reality, consciousness, and the universe at large. Extending this idea beyond our universe, one might contemplate whether similar principles could apply in other realms or dimensions. If conscious observation plays a role in defining reality within our universe, one could speculate about how such interactions might unfold in parallel universes or other dimensions, potentially governed by the same quantum mechanical laws. The implications could suggest that each universe, with its arrangements of particles and conditions, might interact with observers in unique ways, leading to diverse outcomes and realities. Moreover, if we explore the many worlds interpretation, the act of observation takes on a different meaning. Instead of collapsing the wave function to a single reality, observation simply leads to the branching of universes, each representing different outcomes. In this framework, reality is more about the coexistence of all possibilities, with observation serving as a mechanism that differentiates the experiences of observers across multiple realities rather than shaping reality in a singular sense. The role of observation in quantum mechanics raises profound questions about the nature of reality itself. Whether framed through the lens of traditional interpretations or the perspective of parallel universes, the concept challenges our understanding of existence, influencing how we perceive not just our universe, but also the broader cosmos and the interconnectedness of realities that might lie beyond our reach. Quantum foam theory is a concept in theoretical physics that describes the turbulent, fluctuating nature of space-time at extremely small scales, particularly at the Planck scale, where quantum effects dominate. Proposed by physicist John Wheeler, quantum foam suggests that on these minuscule scales, space-time is not smooth and continuous as we perceive it in our macroscopic world, but instead exhibits a frothy, dynamic structure characterized by constant fluctuations and virtual particles popping in and out of existence. This whirling, chaotic tapestry of space-time embodies the idea that the fabric of reality is not static, but instead a tumultuous interplay of quantum events. The relationship between quantum foam and the creation of baby universes emerges from the understanding that fluctuations within this foam can create small regions that detach from our existing universe. In this context, a baby universe refers to a self-contained, nascent universe that evolves independently from our own. These miniature universes might spontaneously form due to the extreme conditions present in the quantum foam, where energy fluctuations could give rise to pockets of space-time that inflate and expand. Such a mechanism suggests that new universes can spawn from the inherent instability present in the quantum realm. The process might be envisioned through the lens of scenarios like cosmic inflation and the multiverse concept. If quantum fluctuations are capable of generating localized regions of high energy and density, these regions could experience rapid expansion, similar to the inflationary phase thought to have occurred in our own universe shortly after the Big Bang. This dimensional and energetic detachment could lead to the emergence of a baby universe, complete with its laws of physics and initial conditions distinct from those in our parent universe. Another intriguing aspect of quantum foam theory is its potential connection to the notion of wormholes or bridges between different regions of space-time. In theory, these pathways could link our universe to a baby universe, suggesting that the quantum foam facilitates the interconnectedness of multiple universes within a broader multiverse framework. If a baby universe were to form and stabilize, it could evolve separately, infinitely expanding new cosmic possibilities beyond our own reality. Ultimately, quantum foam theory provides a tantalizing perspective on the nature of space-time and the potential for new universes to emerge from the intimate fabric of existence. By exploring the foundations of quantum mechanics and its implications for the cosmos, we gain deeper insights into not only the origins of our universe, but also the fascinating possibilities that lie within the quantum realm, hinting at a more complex structure of reality than we might ever fully comprehend. Quantum cosmology is a field that merges the principles of quantum mechanics with the study of the universe's origins and large-scale structure. It seeks to apply quantum theories to cosmological phenomena, particularly to understand how the universe began and evolved. By integrating quantum mechanics into cosmology, researchers aim to investigate fundamental questions regarding the interplay between quantum effects and the fabric of space-time, ultimately shedding light on the nature of the universe itself. One of the key ideas in quantum cosmology is the concept of the universe as a quantum object. In this view, the entire universe is treated as a wave function that encodes all possible states and configurations of the cosmos. This approach enables the exploration of scenarios where classical decays into quantum fluctuations and where multiple outcomes coexist. Central aspects of this framework often include the consideration of quantum gravity, which addresses how gravity behaves at quantum scales and informs our understanding of the early universe. Quantum cosmology provides fertile ground for discussing the existence of multiple universes, particularly through concepts like the multiverse and inflationary cosmology. During the inflationary epoch, a rapid expansion phase theorized to have occurred shortly after the Big Bang, quantum fluctuations could create regions of spacetime that experience different expansion rates. These variations could lead to an array of distinct universes, each with unique physical properties. As a result, quantum cosmology allows for scenarios in which our universe is just one of many, emerging from an underlying quantum framework. Furthermore, some models in quantum cosmology propose that processes like quantum tunneling could lead to the birth of new universes. In these scenarios, regions of spacetime may tunnel from a high-energy state to a lower-energy state, generating separate baby universes that evolve independently from our own. These emergent universes can have different physical constants and fundamental laws, contributing to the broader multiverse notion that includes a diverse spectrum of universes. Overall, quantum cosmology reshapes our understanding of the universe's origins and existence by marrying quantum mechanics with cosmological principles. By exploring themes of quantum fluctuations, tunneling phenomena, and the potential for multiple branching realities, this field invites a more nuanced view of the cosmos, one that embraces complexity and interconnectedness at the most fundamental level, offering profound implications for our understanding of reality itself. Quantum fluctuations are fascinating phenomena that arise from the uncertainty principle of quantum mechanics. This principle asserts that certain pairs of physical properties like position and momentum cannot be simultaneously measured with absolute precision. In a vacuum, where one might expect a complete absence of activity, quantum mechanics reveals that energy levels can fluctuate. These fluctuations can give rise to temporary particles that pop in and out of existence, creating a dynamic landscape of energy at the smallest scales. In some cosmological theories, particularly those relating to the multiverse, these quantum fluctuations are thought to play a key role in the birth of new universes. When energy from a fluctuation reaches a critical threshold, It can lead to a rapid expansion, a process often referred to as inflation. This inflationary epoch could allow a small region of space to exponentially grow, creating conditions suitable for the formation of a new universe. Essentially, a tiny fluctuation in a pre-existing quantum vacuum could be the catalyst for a brand new cosmos. This concept ties into the idea that our universe might not be unique, but instead part of a potentially infinite series of universes, each birthed from different quantum events. Each universe could have its own distinct laws of physics, properties, and dimensions. The fabric of reality at the quantum level may serve as a fertile ground for these diverse creations, allowing for a limitless tapestry of existence. Furthermore, this view challenges our traditional understanding of reality, suggesting that what we perceive as a singular universe could merely be one of countless realms emerging from the fundamental processes of quantum mechanics. This idea invites us to reconsider our place within the cosmos and the nature of existence itself, pushing the boundaries of both science and philosophy in ways previously unimagined. The quilted multiverse theory presents a captivating image of reality, where our universe is just one patch in an extensive cosmic quilt made up of countless other universes. This idea arises from the implications of cosmic inflation, which suggests that during the early moments after the Big Bang, space expanded at an extraordinary rate. If inflation occurred in a manner that was not uniform, it could lead to regions of space continuing to inflate while others have ceased, creating a multitude of separate universes. Each of these universes within the quilt can have its own distinct physical properties and laws of nature. Some may resemble our universe closely, while others could be dramatically different, with varying dimensions, forces, and particles. Because of the vastness of this quilted multiverse, the distances separating these universes can be unimaginably vast, potentially beyond what is observable from our own position in space and time. In this framework, the notion of an observable universe is significant. We are limited to seeing only a small region of the entire multiverse, constrained by the speed of light and the age of the universe. Just beyond our observable horizon, myriad universes could exist, each with its own history and structure, emerging from the same fundamental processes that shaped our own universe. This creates a humbling perspective on reality, as it implies that our understanding of existence is limited to a mere fraction of the entire cosmic tapestry. The quilted multiverse theory raises intriguing philosophical questions about the nature of existence. If there are indeed infinite universes, each with their own set of possibilities, it fuels discussions about fate, randomness, and the very fabric of reality. It challenges us to think beyond the bounds of our universe, suggesting that each patch in the cosmic quilt plays its own unique role in the grand design of the multiverse. The concept of Hubble volumes is essential in understanding the large-scale structure of the cosmos and how it relates to the notion of multiple universes. A Hubble volume refers to a region of space whose size is defined by the distance light travels in a specific time, typically taken over the age of the universe. This volume represents a fundamental scale in cosmology, helping astronomers understand the distribution and behavior of matter and energy within our observable universe. In thinking about multiple universes, the idea of Hubble volumes expands our understanding of cosmic dimensions. Each Hubble volume can be thought of as a distinct area within the universe that exhibits uniform properties on a large scale, as dictated by the cosmological principle, which posits that the universe is homogeneous and isotropic when viewed at great distances. However, if inflationary processes occurred unevenly throughout the cosmos, each Hubble volume might host different regions of space, leading to the possibility of vastly different physical conditions in neighboring regions. This brings us to the concept of a multiverse, where each Hubble volume could not only contain different regions of our single universe, but could also represent entirely separate universes altogether. These universes may undergo their own distinct stages of development, with unique laws of physics and initial conditions. In this scenario, our observable universe is merely one of many potential Hubble volumes, each existing as a unique bubble within a larger multiversal context. The implications of Hubble volumes in relation to multiple universes illustrate how the universe might be far more complex than our daily experiences suggest. While the observable universe is defined by what we can see and measure, the idea of multiple Hubble volumes invites us to consider a broader cosmic framework where infinite variations and possibilities may exist. This perspective not only challenges our notions of reality, but also emphasizes the richness of the cosmos beyond our immediate understanding. The theory of fecund universes offers a fascinating and unconventional perspective on the birth of new universes. Proposed by the physicist Alexander Vilenkin, this theory suggests that universe creation can occur through a process similar to biological reproduction, where one universe gives rise to another. This concept emerges from an exploration of the deep connections between cosmology and quantum physics, particularly in the context of inflation and the multiverse. At the core of the theory is the notion that certain regions of space could undergo rapid inflationary expansion. During this phase, a universe can create daughter universes by dividing and branching off from existing ones. This process might be akin to a budding system in biological organisms, where a new individual emerges from the parent. In the case of the fecund universes theory, it posits that a mature universe rich in quantum fluctuations can create conditions favorable for the emergence of a new universe. These daughter universes could be initiated by local instabilities that trigger their own inflationary phase, effectively giving rise to separate self-contained cosmic entities. What makes this theory particularly intriguing is the implication that the properties and laws of these newly formed universes could vary significantly from the parent universe. Each daughter universe might have different physical constants, dimensions, or even entirely distinct rules governing their behavior. This notion leads to a potentially infinite series of universes, each generating its own progeny, further expanding the vast landscape of multiversal possibilities. Furthermore, the theory of fecund universes interweaves cosmology with fundamental questions about the nature of existence. It prompts us to think about the origins of our universe within a broader contextual framework and challenges our traditional understanding of creation. By adopting a reproductive lens for universe formation, this theory not only enhances our comprehension of the cosmos, but also provokes deeper reflection on the interconnectedness of all underlying cosmic processes. Lee Smolin's concept of cosmic natural selection introduces a thought-provoking approach to understanding how universes might evolve over time. Drawing an analogy from biological evolution, Smolin proposes that universes undergo a process of natural selection, where the properties of a universe influence its ability to produce offspring universes. This perspective builds on the idea that the conditions and constants within a universe can strongly affect its capacity for star formation, subsequently leading to the creation of black holes, which can serve as the seeds for new universes. In Smolin's framework, when a black hole forms in a universe, it can give rise to a new universe with potentially different physical laws and constants. This new universe may be influenced by the characteristics of its parent universe, but it can also develop variations that enhance its own survival prospects. The universes that are best suited for generating black holes are those that can sustain processes such as star formation for longer periods. Over time, this leads to a sort of evolutionary process, where the fittest universes, those that are more likely to create black holes, are more successful in giving rise to offspring. The implications of cosmic natural selection are profound. If this process is valid, it suggests that the fundamental constants we observe in our own universe could be the result of historical evolutionary pressures from previous parent universes. This idea challenges the traditional view that these constants are fixed and unchanging, opening the door to the possibility that they are instead the product of a cosmic lineage shaped by the survival of the fittest universes through multiple generations. Moreover, this perspective invites deeper questions about the nature of existence and the interconnectedness of universes across the multiverse. Just as species in biology adapt to their environments, universes could similarly adapt through the selective pressures of their evolutionary histories. Smolin's theory not only enriches our understanding of cosmic evolution, but also integrates concepts from physics with the principles of evolution, creating a compelling narrative about the ongoing journey of universes through time. Max Tegmark's mathematical universe hypothesis proposes a bold and intriguing idea that the universe and everything within it can be understood entirely through mathematics. According to Tegmark, every mathematical structure exists, and those that have the right complexity manifest as physical realities. This perspective contends that all conceivable mathematical forms correspond to actual physical universes, suggesting that mathematical existence is as authentic as physical existence itself. This hypothesis implies that our universe is just one of an enormous array of potential universes, each represented by different mathematical structures. These mathematical entities can encompass universes with completely different physical laws, constants, and dimensions. By positing that reality is fundamentally mathematical, Tegmark invites us to view the multiverse as an extensive tapestry woven from an infinite collection of mathematical forms. Each universe in this multiverse corresponds to a unique mathematical structure that can exist in its own right. In relation to the multiverse concept, Tegmark's hypothesis takes a radical stance, suggesting that every possible universe, regardless of how bizarre or counterintuitive its properties may be, is realized in some mathematical form. This means that there could be universes governed by entirely different rules of physics, or even universes where logic and causality operate in unexpected ways. The implications of this idea challenge our traditional understanding of existence and the constraints we often place on reality. By merging mathematics and physics so closely, Tegmark elevates the role of mathematics from a mere tool for describing the universe to a foundational component of its very fabric. This perspective not only enriches our exploration of the multiverse, but also prompts deeper philosophical questions about the nature of reality and existence itself. Ultimately, it suggests that the cosmos is far more diverse and intricate than we can perceive, with infinite possibilities waiting to be uncovered through the lens of mathematics. The many bubbles interpretation of quantum mechanics presents a distinctive approach to quantum phenomena, diverging from the well-known many worlds interpretation. While both theories grapple with the implications of quantum mechanics, particularly concerning superposition and entanglement, they offer different views on how reality unfolds at the quantum level. In the many worlds interpretation, proposed by Hugh Everett III, the universe continually splits into multiple branches or worlds for every possible outcome of a quantum event. This means that every time a quantum event occurs, such as a particle being in multiple states, the universe divides into separate, non-communicating branches, each representing a different outcome. Essentially, all outcomes are realized, creating a vast multiverse of parallel worlds where every possibility plays out simultaneously, albeit in different branches of reality. On the other hand, the many bubbles interpretation, developed by cosmologist Alexander Vilenkin and others, suggests a more visual and conceptual framework. In this view, the universe is likened to a vast cosmic foam made up of countless bubbles. Each bubble represents a distinct universe that originates from a different quantum fluctuation within a primordial quantum vacuum. Unlike the many worlds interpretation, which focuses on branching timelines from singular events, the many bubbles interpretation emphasizes the creation of multiple universes from spontaneous fluctuations in a shared quantum landscape. These bubbles may undergo their own unique evolutionary paths and might contain different physical properties or constants. While the many worlds interpretation emphasizes the isolation of universes branching from measured outcomes, the many bubbles approach highlights the collective creation of universes from quantum fluctuations and inflationary processes. This distinction offers a broader perspective on how universes might arise and coexist, framing reality not only as a series of divergent paths, but as a dynamic and expansive realm of cosmic bubbles formed from the fabric of quantum realities. The simulated universe theory posits that our perceived reality could be a sophisticated computer simulation rather than an objective physical existence. This concept has gained traction in both scientific and philosophical discussions, largely due to advancements in technology, artificial intelligence, and our understanding of virtual and augmented realities. Advocates of this theory, including prominent figures like philosopher Nick Bostrom, suggest that if it becomes possible to create simulations indistinguishable from reality, it is plausible to consider that we might already exist within such a creation. This theory raises intriguing implications regarding the nature of reality and consciousness. If we are indeed living in a simulation, it brings forward questions about the existence of the creators, potentially advanced beings or civilizations capable of constructing such elaborate environments. The simulated universe theory also posits that if a single advanced civilization can create simulations, there could be countless simulations existing concurrently, leading to a multiverse of simulated realities. In this view, each simulation could be designed with different laws of physics, rules, and experiences for its inhabitants, fostering a vast landscape of alternative realities. Furthermore, this theory interacts with the concept of multiple realities by suggesting that each simulation represents a distinct universe with its own parameters and histories. For instance, a civilization might run multiple simulations, each representing different scenarios, outcomes, or choices, allowing for exploration of various paths without altering the actual base reality of its creators. Consequently, this gives rise to a multiverse not just in the conventional sense, but as a continuum of simulated experiences, creating an intricate web of realities spanning beyond our individual perceptions. Reflecting on the simulated universe theory pushes the boundaries of our understanding of existence. If we are indeed living within a simulation, it invites deeper philosophical inquiries into the nature of consciousness, reality, and what constitutes real experience. Whether in a simulated or physical universe, the interconnectedness of possible outcomes and realities opens up a profound dialogue about our place in the cosmos and the potential paths that existence can take. Modal realism is a philosophical theory that proposes the existence of many possible worlds that are just as real as the actual world we inhabit. According to modal realists, every way a world could possibly be corresponds to an actual world existing in its own right. This perspective allows for the consideration of myriad alternative scenarios, where different choices, events, or circumstances create distinct realities, each equally valid and real. The connection between modal realism and the multiverse in physics arises from the idea that the many possible worlds discussed in modal realism can parallel the concept of multiple universes in theoretical physics. In many interpretations of quantum mechanics, such as the many worlds interpretation, each quantum event can lead to the creation of a separate universe, where every possible outcome occurs. This echoes the modal realist notion that every conceivable situation corresponds to an actual world. Both frameworks explore the implications of alternatives, whether through philosophical reasoning or physical theory. Moreover, both modal realism and the multiverse concept challenge the traditional notion of a single, unique reality. They invite us to consider existence beyond our immediate experience, suggesting that what we perceive as actual might be part of a much broader landscape of realities. While modal realism philosophically articulates the status of possible worlds, the multiverse hypothesis provides a framework for understanding the fundamental structure of reality at a physical level. The intersection of these two ideas raises additional questions regarding the nature of existence, causality, and the implications for our understanding of choice and agency. For instance, if all possible worlds exist as modal realism suggests, how does that relate to the scientific theories proposing that different outcomes branch into separate universes? This philosophical and scientific dialogue invites deeper reflection on the nature of reality and the many layers of existence that may lie beyond our current understanding, revealing a multifaceted tapestry of worlds that challenge our views of what it means to exist. The parallel lives interpretation of quantum mechanics offers an intriguing viewpoint on how quantum events unfold, positing that every possible outcome of a quantum event unfolds in an alternate parallel life or timeline for each individual involved in the decision. While this idea aligns with the general concept of multiverses found in quantum mechanics, it differs from the many worlds interpretation in significant ways. In the many worlds interpretation, originally formulated by Hugh Everett III, the universe continually splits into numerous branches with every quantum measurement or event. Each possible outcome of a quantum event occurs in a separate, non-communicating universe, creating a vast multiverse where all realities coexist simultaneously. This interpretation asserts that every conceivable outcome is realized in its own distinct universe, with no inherent connection between the different branches except their shared origin. In contrast, the parallel lives interpretation emphasizes the personal experience of individuals involved in quantum events. It suggests that, instead of the universe splitting apart into separate branches, individuals experience distinct outcomes along separate paths. In this view, every person leads parallel lives corresponding to different decisions, experiences, or outcomes dictated by quantum randomness. Therefore, while the many worlds interpretation produces entire universes that diverge from each other, the parallel lives interpretation focuses more on how individuals navigate these divergent paths within their own lives. This distinction opens up unique philosophical discussions regarding identity, choice, and the nature of consciousness. The parallel lives interpretation invites consideration of how our decisions might create a tapestry of experiences that explore various outcomes, even as we remain unaware of the myriad possibilities in which we might exist. Overall, while both interpretations explore the implications of quantum mechanics and alternate realities, they approach these fascinating concepts from different angles, contributing to a rich dialogue within the philosophy of science. The theory of quantum suicide and immortality is a thought-provoking concept arising from the principles of quantum mechanics, particularly when viewed through the lens of the many worlds interpretation. This theory posits a hypothetical scenario where an individual conducts a series of experiments that involve making choices leading to outcomes that could result in their death or survival. The pivotal notion is that, in the many worlds framework, every possible outcome occurs in a separate branch of the universe. In a quantum suicide experiment, the person would engage in a mechanism like a quantum device that has a probability of causing fatal outcomes based on quantum events, such as the decay of a particular radioactive atom. According to the rules of quantum mechanics, if the person were to repeat this experiment multiple times, each outcome, whether survival or death, would spawn a split in the universe. In one branch, the individual survives, while in another they do not. Therefore, while the individual experiences the outcomes of survival in one branching world from a third-person perspective, they could be regarded as experiencing a form of immortality, since they will always survive in at least one branch of the multiverse. This theoretical framework challenges our conventional understanding of mortality and consciousness. If the many worlds interpretation is accurate, one could argue that no matter how many times a quantum suicide experiment is conducted, the individual is capable of continuing to exist in the branches where they survive. This leads to the paradoxical conclusion that, in these surviving branches, they are effectively immortal, as they will never experience a definitive death from their own point of view. The implications of quantum suicide and immortality foster profound questions about identity, existence, and the nature of consciousness across multiple realities. It invites us to consider the interconnectedness of quantum events and their outcomes, as well as the complicated relationship between our lived experiences and the vast multiverse that may arise from those very events. While largely theoretical and philosophical in nature, this idea underscores the rich interplay between quantum mechanics and the broader concepts of existence and reality. The cyclic model of the universe is a fascinating cosmological framework that proposes an eternal sequence of cosmic expansions and contractions, effectively suggesting that the universe undergoes endless cycles of birth, evolution, and rebirth. In this model, the universe expands from a hot, dense state, similar to the Big Bang, until it reaches a maximum size, at which point it begins to contract back into a singular state before repeating the cycle again. This cyclical process allows for a dynamic universe without a definitive beginning or end, challenging traditional views of a singular one-time creation. This model suggests the potential existence of universes beyond our own by positing that each cycle could represent a different iteration of the universe. As the universe transitions through expansions and contractions, its properties, physical laws, and even dimensions could change with each new cycle. In this way, what we understand as our universe might merely be one phase in an ongoing series of universes, each emerging from the remnants of the last. The transitions between these phases could give rise to diverse realities, with each cycle potentially yielding unique characteristics. The cyclic model interacts with ideas from inflationary cosmology, which explores how rapid expansion could create bubble-like structures in a larger multiverse scenario. As each phase of contraction could lead to quantum fluctuations, these fluctuations might trigger new Big Bangs, resulting in the formation of entirely new universes that exist alongside or perhaps emerge from our own on a larger cosmic scale. Thus, the cyclic model suggests that not only is our universe currently in one of many possible iterations, but that it is also part of a much grander framework of cosmic evolution. The implications of the cyclic model provoke profound questions about our understanding of time, reality, and existence itself. It invites us to consider how universes might emerge, evolve, and coexist, pushing the boundaries of our knowledge while deepening the exploration of the cosmos. If these cycles continue indefinitely, then the universe can be viewed not as a solitary existence, but as a meaningful participant in an eternal cycle, with countless realities potentially existing within its expansive framework. The Big Bounce theory presents an intriguing alternative to the traditional Big Bang model of the universe, proposing that our universe is part of an ongoing cycle of expansions and contractions rather than having originated from a singular beginning. In this framework, the evolution of the universe is characterized by a series of bounces where the universe undergoes a period of contraction, reaching a highly dense state before bouncing back and expanding again. This perspective allows for the idea that there could be universes that existed before our current one, and that future universes may follow its eventual demise. According to the Big Bounce theory, as the universe contracts to a state of extreme density, which may resemble a singularity, it does not necessarily end. Instead, this contraction leads to conditions that facilitate a rebound, triggering a new expansion phase akin to the Big Bang. This process creates a continuous cycle, wherein each collapse gives rise to a subsequent universe. In this context, our universe is simply one phase in this unending sequence of cosmic evolution. The implications of the Big Bounce theory suggest that there were indeed universes that existed prior to our own, each contributing to the rich tapestry of cosmic history. These previous universes may have had different physical properties, laws, or dimensions, thereby enriching the landscape of existence. Furthermore, this model inspires the concept that our universe is not unique, but rather part of a broader universe that has been cycling through time for potentially infinite ages. Additionally, the Big Bounce can integrate ideas from quantum gravity, which explores how gravitational effects influence the behavior of the cosmos at the smallest scales. This merging of concepts invites a deeper understanding of how the universe transitions between contraction and expansion, and how these transitions could lead to new realities. The Big Bounce theory not only challenges our perceptions of the universe's origin, but also opens up profound questions about the nature of time and existence, allowing for the possibility of a cosmos filled with countless universes that have risen and will rise anew through the eternal cycles of cosmic evolution. Roger Penrose's conformal cyclic cosmology is a distinctive cosmological model that proposes an innovative way to understand the evolution of the universe through a series of infinite cycles, where each cycle is referred to as an eon. In this framework, Penrose suggests that the universe undergoes a process where the end of one eon transitions seamlessly into the beginning of another. Unlike the traditional models that often emphasize a singular Big Bang event, conformal cyclic cosmology presents a picture in which the universe evolves through repetitive phases of expansion and transformation. At the heart of this theory is the concept of conformal geometry, which allows for the simplification of the universe's structure. As the universe expands and cools, the scales and distances become less significant, and the detailed physical properties of matter gradually diminish. Penrose proposes that at the end of an eon, when the universe is predominantly empty and features only low-energy radiation, its structure becomes more simplified and can be described by a conformal framework. Time and space lose their typical characteristics, leading to a state of cosmological recycling that serves as a bridge to the next eon. Once the universe reaches this state, Penrose theorizes that the information encoded in the gravitational waves and the dynamics of the previous eon can affect the formation of new structures in the subsequent eon. Thus, while the matter content of each eon appears completely distinct, the underlying geometry and features of spacetime are continually carried over from one cycle to the next, enabling the evolution of new galaxies and cosmic phenomena. Conformal cyclic cosmology functions as a compelling alternative to both traditional Big Bang models and the concept of an eternal universe. By suggesting an infinite series of connected eons, Penrose's theory broadens our understanding of cosmic history. This model also proposes that the universe is not merely a one-time event, but engages in a profound interplay of beginnings and endings, emphasizing a dynamic and continuous nature that transcends conventional time. Through this lens, each eon is viewed as a chapter in the greater cosmic narrative, one that may contain echoes of its predecessors while forging an inventive path into the future. The oscillating universe model is a cosmological framework that proposes the universe undergoes a continuous series of expansions and contractions, leading to cyclic phases of creation and destruction. According to this model, after a period of expansion, the universe reaches a peak size and then begins to contract, ultimately collapsing back into a singular state before rebounding into another expansion phase. This periodic process allows for the possibility of multiple universes existing over time, each representing different iterations of cosmic evolution. In this model, each cycle can be thought of as a distinct universe with varying physical conditions and structures. When the universe contracts, it might lose the specific properties and information of the prior phase, giving rise to new conditions and characteristics upon rebirth. Each oscillation can result in a universe that differs from the previous one, influenced by the dynamics of its contraction and the conditions surrounding its subsequent expansion. This creates a diverse array of universes, each of which retains some echoes of its predecessors while evolving in new and potentially unexpected ways. The idea of multiple universes over time is also supported by the notion of quantum fluctuations that could occur during the expansion phases. If different states of matter, energy, and fundamental constants emerge during these fluctuations, it opens the door for entirely new types of universes to form in each cycle. Consequently, while our current universe may appear singular, it can be viewed as one instance within a vast sequence of oscillating realities. Moreover, the oscillating universe model challenges the notion of a fixed beginning or end to the cosmos. Instead, it suggests a dynamic and ongoing process where universes are born, evolve, and eventually fade, only to be replaced by new ones. This cyclical nature can imply that the universe is not just an isolated existence but part of a larger cosmic rhythm, capable of nurturing a multitude of universes throughout the vastness of time. Thus, the oscillating universe model contributes to our understanding of cosmic evolution by portraying a rich tapestry of realities that unfold across endless cycles. The emergent cyclical inflation model presents an intriguing perspective on the origins and evolution of our universe. It suggests that the cosmos does not follow a simple one-off beginning, but instead goes through alternating phases of expansion and contraction. This model fuses the concept of inflation, which is an extremely rapid expansion of space that occurred shortly after the Big Bang, with the idea that the universe has undergone multiple cycles of such phases throughout its existence. In this framework, each cycle begins with a period of inflation that exponentially stretches space, smoothing out any irregularities and creating a uniform universe. Once this inflationary phase ends, the universe enters a contraction phase, eventually collapsing back into a highly dense state. The cyclical nature of this model posits that after reaching this dense state, a new inflationary phase begins, and the whole cycle repeats. This mechanism suggests a universe that eternally transforms, creating and recreating itself in a rhythmic dance of expansion and contraction. One of the key advantages of the emergent cyclical inflation model is its ability to address some of the mysteries surrounding the Big Bang and cosmic inflation. For instance, it can provide explanations for the homogeneity and isotropy observed in the universe today without relying solely on a single explosive event. This continuous cycle could also help to resolve certain issues related to dark energy and the ultimate fate of the universe. As scientists continue to explore this model, it stirs up thought-provoking questions about the nature of time, space, and the underlying structure of reality itself. The merging of inflationary theory with a cyclic cosmic framework presents a fascinating narrative that challenges traditional concepts and opens up new avenues for understanding the universe and our place within it. In cyclic universe models, the concept of entropy, which is essentially a measure of disorder within a system, presents a significant challenge. According to the second law of thermodynamics, entropy tends to increase over time in an isolated system, suggesting that the universe should experience a gradual decline into disorder. As we envisage a universe that undergoes endless cycles of expansion and contraction, addressing how entropy is managed throughout these transitions becomes crucial. One approach is to consider that at the beginning of each cycle, when the universe inflates from a highly dense state, the entropy resets. This reset effectively allows the universe to begin anew, creating conditions that could support complex structures and life without facing the consequences of accumulated entropy from the previous cycles. Such a mechanism might involve the idea that, upon contraction, all matter and energy are compressed, and during the subsequent inflation, the universe emerges with a fresh, low-entropy state. Another intriguing aspect revolves around the potential for entropy to redistribute during the cycle. Instead of simply building up indefinitely, the contraction phase can, in theory, allow for entropy to reorganize. As the universe collapses, it might convert some of that accumulated disorder into new forms of order during the inflation that follows. This process implies an intricate dance where the universe balances entropy through the cyclical transitions, continuously allowing the emergence of structured systems. Moreover, researchers explore additional mechanisms that could facilitate these transitions. Concepts like quantum gravity or modifications to traditional thermodynamic laws within the context of a cyclic universe may offer an opportunity to rethink how entropy is perceived and managed. These innovative ideas suggest a more dynamic and multifaceted understanding of entropy, one that accommodates the peculiarities of a universe that is forever cycling through expansive and contracting phases. Observational evidence plays a pivotal role in validating or challenging theories about the universe, including cyclic universe models. One of the crucial aspects these models aim to explain is the cosmic microwave background radiation. This remnant glow from the early universe provides a snapshot of its state shortly after the Big Bang. If a cyclic universe has undergone multiple expansions, astronomers may expect to find specific signatures within this background radiation that indicate repetitious patterns consistent with successive cycles. Any anomalies or irregularities in the temperature fluctuations of this radiation could furnish insights into whether we live in a cyclical cosmological setting. Another facet to consider is the distribution of galaxies and large-scale structures in the universe. Observations of these formations can reveal patterns within the cosmic web. If the universe is indeed cyclic, we might anticipate finding structures that exhibit characteristics indicative of repeated expansions and collapses. This pattern could present itself in the way galaxies group together or in the voids that exist between them. Cosmic structures shaped by past cycles would create specific statistical signatures that could be discerned through extensive surveys of the night sky. Furthermore, the nature of dark energy remains a critical area of investigation. Understanding how this enigmatic force impacts the expansion of the universe enhances our grasp of cosmic dynamics. If cyclic models are accurate, we might witness variations in the influence of dark energy as the universe transitions between its expansion and contraction phases. Monitoring these changes could help either support or refute the idea of a cyclic universe. Finally, gravitational wave detection offers a cutting-edge method for gathering evidence. Gravitational waves produced during cosmic events might leave traces that align with the predictions of cyclic models. If such waves appear with particular frequencies or patterns expected from previous cycles, it could bolster the case for a cyclic universe. Each of these observational avenues reflects the potential richness of evidence that could ultimately confirm or challenge the cyclic universe theories, adding depth and excitement to our attempts at understanding cosmic evolution. Cyclic models offer distinctive perspectives on the initial singularity problem, which poses significant challenges for traditional cosmological theories. The initial singularity refers to the point in time at the very beginning of the universe, characterized by infinite density and temperature, where our current understanding of physics breaks down. Cyclic models seek to circumvent this predicament by proposing a universe that does not begin with a singular event, but instead involves a series of cycles of expansion and contraction. In this framework, rather than emerging from a singularity, the universe is envisioned as having existed eternally, continually transitioning through epochs of rapid expansion or inflation, followed by collapse. Each cycle begins from a highly dense state, but crucially, this state does not imply an infinite singularity in the classic sense. Instead, it represents a finite volume of matter and energy. The transition from contraction to expansion in these models suggests that the universe smoothly evolves without encountering infinite physical quantities. Additionally, some cyclic models incorporate ideas from areas such as string theory and quantum gravity, which offer modified understandings of fundamental forces and particles. These theories suggest that at extremely high densities, different physical behaviors can emerge, allowing for the breakdown of classical notions of singularities into more manageable phenomena. This includes the possibility of a bounce, where the universe contracts to a point and then rebounds into a new phase of expansion, a behavior that helps delineate the boundaries of a singularity. Finally, cyclic models invite us to consider the nature of time itself. Rather than thinking of time as having a singular beginning, these models propose a framework in which time is cyclical. This reimagining of time allows for a universe that is filled with periodic phases, challenging traditional concepts and opening doors to the idea that the universe has no true beginning or end, but rather a series of interconnected cycles that define its existence. The concept of time before time in cyclic universe models is a fascinating idea that challenges conventional notions of temporal beginnings. In a traditional understanding, time is often thought to have started with the Big Bang, marking a distinct point where both the universe and time itself began. However, cyclic models propose that this perspective is limited and suggest that time may not have a singular starting point in the way we typically conceive it. In the context of cyclic universes, time before time implies the existence of epochs or phases that occurred prior to our current cosmic expansion. As these models suggest, the universe might go through an eternal series of cycles of expansion and contraction, where each cycle represents a different phase of existence. If the universe continually undergoes this cyclical behavior, then it follows that both space and time have been in a dynamic dance, perpetually looping through multiple instances of before and after. This idea invites us to reevaluate our understanding of causality and the nature of reality. In these models, time does not start at the Big Bang but is inherently tied to the entire history of the universe's cycles. Each contraction phase leads to a new expansion phase, suggesting that there are moments that precede what we currently identify as now. In a sense, time could be seen as a continuum without a definitive beginning, where past cycles lay down the groundwork for current cosmic phenomena. Moreover, concepts from quantum gravity and string theory may further inform our understanding of this time before time. These theories encourage the exploration of conditions under which time may behave differently at extremely high energies and densities, allowing for possibilities beyond our standard perceptions of time and space. Thus, the cyclic universe models present an intriguing narrative that intertwines time with the fabric of the cosmos itself, suggesting a universe with a rich, layered temporality that transcends singular beginnings. Cyclic universe models provide a compelling backdrop for discussions surrounding the anthropic principle, which posits that the universe must have properties that allow for the existence of observers, such as humans. This principle offers various interpretations, but at its core, it suggests that the observed universe is fundamentally aligned with the conditions required for life and consciousness to emerge. In the context of cyclic models, the anthropic principle takes on a unique dimension, as it proposes that the universe and its laws have evolved through potentially countless cycles. One way cyclic models engage with the anthropic principle is by suggesting that each cycle of the universe could create conditions that favor the emergence of complex structures and life. As the universe undergoes expansion and contraction, it forms galaxies, stars, and planets, giving rise to environments where life may flourish. The anthropic principle can thus be invoked to argue that we find ourselves in a universe capable of supporting life precisely because other configurations during previous cycles may have been less hospitable, leading to a selective survival of universes that eventually produced observers. Moreover, cyclic universe models imply a diverse range of cosmological conditions that could appear across cycles. Each iteration could result in various physical properties, allowing for a multitude of universes, each with different parameters. The anthropic principle can then facilitate the idea that we exist in one of those universes with life-permitting characteristics, while many others may not host intelligent life. This perspective aligns with the idea of a multiverse, where our universe is just one of many, influenced by the preceding cycles. Additionally, some cyclic models explore the possibility of different cosmic laws or forces evolving or morphing during each cycle. This variability introduces the concept that the specific conditions we observe today may be the result of numerous cycles, honing and refining the universe into a form suitable for supporting conscious beings. This interaction between cyclic cosmology and the anthropic principle suggests that not only does the universe evolve, but it also does so in a manner that can influence the likelihood of conscious life arising, reinforcing the delicate connection between cosmic evolution and our existence within it. Laws of physics in regions beyond our observable universe are a topic of speculation and intrigue among cosmologists. Our observable universe is limited to a specific volume of space that we can study through light and other signals that have had time to reach us since the Big Bang. Beyond this boundary lies a vast expanse, the nature and properties of which remain largely unknown. The potential for differing physical laws in this unobserved region raises fascinating possibilities for our understanding of reality. One concept to consider is that the laws of physics may not be uniform throughout the entire cosmos. Theories such as inflation suggest that different regions of the universe may have undergone varying conditions during their formation, potentially leading to regions where physical constants and fundamental forces differ. In these distant areas, phenomena such as the strength of gravity, electromagnetic interactions, or even the behavior of fundamental particles could manifest uniquely, resulting in fundamentally different physical laws than those we observe. Additionally, some speculative theories propose the existence of a multiverse, wherein our universe is just one of many, each governed by its own set of physical laws. In such a framework, regions beyond our observable universe might exist in other bubble universes that are completely detached from our experience. If this multiverse hypothesis holds true, the laws that we consider constant could be mere local constructs that apply within our own universe, while allowing for a vast variability in other universes. This notion expands the complexity of the cosmos and challenges our fundamental understanding of stability and order. Moreover, the nature of time and space themselves may behave differently in regions beyond our current observational limits. The influence of cosmic inflation suggests that certain physical phenomena, such as the behavior of quantum fields, might showcase different characteristics in unobserved regions due to the effects of extreme curvature or other unknown factors. These variations could significantly alter fundamental interactions, leading to a tapestry of realities that would be unrecognizable from our local perspective. Ultimately, the prospect of differing laws of physics in regions beyond our observable universe challenges our perceptions and invites us to rethink the scope of the cosmos. As scientific exploration continues and new theories emerge, understanding these unknown realms may reshape our view of reality and fundamentally transform our concepts of space, time, and the laws that govern them. The fine-tuning problem refers to the startling observation that the fundamental physical constants of our universe are remarkably well suited for the existence of life. If these constants, such as the strength of gravitational and electromagnetic forces, were even slightly different, the universe would be inhospitable to the complex structures necessary for life as we know it. This precise adjustment raises profound questions about why our universe demonstrates such resilience, leading to discussions about the underlying mechanisms that could account for this remarkable balance. One potential explanation for this fine-tuning issue is the multiverse hypothesis. In this framework, our universe is just one of an immense collection of universes, each with its own set of physical constants and laws. This vast ensemble allows for a diverse range of conditions, many of which would not support life at all. The multiverse theory posits that among this multitude of universes, it is statistically likely that some will have the precise conditions needed for life to emerge. The multiverse addresses the fine-tuning problem by shifting the perspective from a single universe to a broader cosmological context where life-friendly conditions are just one outcome of many possibilities. This vast array of differing physical constants suggests that while our universe is finely tuned, it is simply one of many realms where such tuning may occur by chance. Thus, the existence of observers like us becomes more plausible, as we naturally find ourselves in a universe that permits life, while other, more hostile universes remain unobserved and uninhabited. Additionally, some versions of the multiverse theory propose mechanisms that could lead to the divergence of constants. For instance, certain theories of cosmic inflation or string theory might suggest that different regions of space undergo unique processes that impact their physical characteristics. As a result, the multiverse not only provides a potential solution to the fine-tuning problem, but also prompts deeper inquiries into the fundamental nature of reality. By considering our universe as part of a broader tapestry, scientists explore how these variations in constants might be inherent to the very fabric of the cosmos. The strength of fundamental forces in different universes can vary significantly due to the diverse physical conditions and properties that may exist in the multiverse framework. In our universe, the four primary fundamental forces, gravitational, electromagnetic, weak nuclear, and strong nuclear forces, exhibit specific strengths that are finely tuned, allowing for the emergence of matter, stars, galaxies, and ultimately life. However, in other universes, these forces could manifest very differently, leading to unique cosmic structures and phenomena. One potential source of variation in the strength of these forces lies in the constants associated with them. For instance, The gravitational constant determines the strength of gravitational interactions, while the coupling constants for electromagnetic and nuclear forces dictate how particles interact at the fundamental level. In a multiverse scenario, these constants could take on different values in other universes due to the varying conditions that prevailed during their formation. This randomness might result in some universes where gravity is incredibly weak, preventing the formation of stars and galaxies, while others might have strong nuclear forces so robust that they prohibit the existence of stable atoms. Another aspect of force variability involves the underlying physical laws and symmetries that govern these interactions. Concepts from string theory, for instance, suggest that our familiar forces could arise from the vibrations of fundamental strings in extra dimensions. If these extra dimensions have different configurations in alternate universes, the fundamental forces of those universes might be engineered by different vibrational modes. This could lead to conditions in which forces behave differently or are expressed in novel ways, creating a rich tapestry of potential physical realities. Additionally, the environment and initial conditions of different universes could play a significant role in determining how forces manifest. Factors such as the energy density, temperature, and dimensional structure may influence the dynamics of fundamental interactions. For example, in a universe dominated by high-energy phenomena, the relationship between forces could change drastically compared to our low-energy universe, leading to distinctive structures and possibly exotic forms of matter. Overall, the idea that the strength of fundamental forces could vary across different universes invigorates our understanding of physical laws and their foundations. By exploring these variations, scientists can contemplate the breadth of cosmic possibilities and recognize how finely tuned conditions are necessary for the unique characteristics of our own universe. Such investigations not only challenge our existing paradigms, but also deepen our quest for understanding the fundamental nature of reality. Variable speed of light cosmology presents a bold rethinking of one of the cornerstone principles of modern physics, the constancy of the speed of light. Traditionally, according to Einstein's theory of relativity, the speed of light in a vacuum is always constant and serves as a universal limit for the transfer of information and energy. However, proponents of variable speed of light theory suggest that this speed may not be constant throughout all time and space, particularly during key events in the early universe, or in different universes altogether. In this cosmological framework, the speed of light could have changed over cosmic history, particularly during rapid expansion periods such as cosmic inflation. Such variations could help explain some of the observed characteristics of our universe, such as its large-scale structure and the uniformity of the cosmic microwave background radiation. For instance, if the speed of light was significantly higher during the very early moments following the Big Bang, it could facilitate faster information transfer across expanding regions, leading to a more homogeneous universe. When applying the concept of variable speed of light to other universes, it opens intriguing possibilities regarding the fundamental nature of physical laws. In a multiverse scenario, each universe could operate under different parameters, including varying physical constants such as the speed of light. As a result, those universes might host a diverse array of physical laws that allow for different forms of matter and energy interactions. For example, a universe with a variable speed of light might see the emergence of gravitational phenomena or other interactions that differ significantly from those in our own universe. Moreover, variable speed of light cosmology could provide explanations for phenomena that challenge conventional physics, such as dark energy and dark matter. If light behaved differently in different regions or universes, it might alter gravitational interactions, affecting how matter clusters and behaves on cosmic scales. Such variations could lead to distinct structures forming in those universes, creating a dynamic landscape of cosmic evolution. The exploration of variable speed of light cosmology invites a more flexible understanding of the fundamental constants and laws that govern the universe. It encourages scientists to question the rigidity of physical principles as they investigate the vast potentialities across different universes. addressing not only the character of our own cosmos, but also the realms that lie beyond our observational capabilities. The ratio of dark energy to dark matter is a fundamental element of our current cosmological model, which plays a crucial role in describing the universe's expansion and the behavior of its large-scale structure. In our universe, dark energy is thought to make up about 70% of the total energy content, while dark matter accounts for roughly 26%, with ordinary matter constituting only about 4%. However, in other universes, this balance could vary significantly, leading to markedly different cosmic dynamics and structures. In universes where the ratio of dark energy to dark matter differs, the nature and effects of cosmic expansion would also change. If a universe had a higher proportion of dark energy, it might experience accelerated expansion at a more pronounced rate. This could lead to a cosmos that expands too rapidly for galaxies and structures to form coherently, potentially resulting in a vastly different arrangement of matter, or even in the development of myriads of isolated galaxies. Conversely, if dark matter predominated over dark energy, gravitational attraction could dominate, leading to a universe that decelerates, has a more clustered distribution of matter, and ultimately experiences a different fate, possibly collapsing back on itself. Moreover, the characteristics of dark energy and dark matter themselves might also vary in alternate universes. Different physical constants or laws could lead to variations in the composition and behavior of these entities. For instance, if dark energy were fundamentally altered, it might not produce the same repulsive force that drives accelerated expansion in our universe. The resulting dynamics could produce entirely new forms of cosmic evolution, impacting star formation, galaxy interactions, and the overall development of structures. The implications of varying dark energy and dark matter ratios extend to the formation of life and complex structures as well. In a universe where dark energy dominates excessively, life-supporting environments would be scarce. On the other hand, universes with different and balanced ratios could foster conditions conducive to complex organisms, depending on how star and galaxy formation play out in those contexts. By considering alternate ratios of dark energy to dark matter in other universes, cosmologists can explore the broader implications of our universe's configuration. This investigation helps illuminate the forces shaping our cosmic landscape, while highlighting the extraordinary diversity of potential realities that could arise from different fundamental properties and interactions. The anthropic principle is a philosophical and scientific consideration that explores the conditions necessary for the existence of intelligent life and observers within the universe. It posits that the universe must exhibit specific properties and parameters that allow life to emerge simply because we exist to observe it. The anthropic principle suggests that the observed fine-tuning of the universe is not coincidental, but rather a reflection of the constraints imposed by the presence of conscious beings like ourselves. This principle can be particularly powerful when discussing the concept of multiple universes or the multiverse theory. In a multiverse scenario, there exists an immense collection of universes, each potentially governed by different physical laws and constants. If such a multiverse exists, it implies that our universe could simply be one of a myriad of possibilities, some of which may not support life due to unfavorable conditions. The anthropic principle plays a crucial role here, as it suggests that we are more likely to find ourselves in a universe with properties conducive to life, simply because we could only be asking these questions in a universe that allows for our existence. In this context, the anthropic principle provides a compelling explanation for the apparent fine-tuning of various physical constants. By recognizing that there are countless other universes with different configurations, the principle implies that it is not surprising that at least one universe, like ours, has the right conditions for life. This reasoning establishes a connection between the distinct properties of our universe and the broader framework of cosmic possibilities, providing a statistical basis for our existence. Moreover, the anthropic principle invites philosophical reflection on the nature of reality. It raises questions about purpose, existence, and the fundamental nature of the cosmos. If multiple universes with diverse physical laws exist, what does that imply about the nature of our own universe and our place within it? This exploration deepens our understanding of not just the physical universe, but also the larger existence of life and consciousness within a potentially infinite cosmic landscape. Ultimately, the anthropic principle and the idea of multiple universes intersect in a way that reshapes our interpretations of reality and the conditions required for life as we know it. Different values for physical constants can substantially influence the formation of complex structures in other universes, dictating everything from the behavior of fundamental forces to the stability of atoms. Physical constants, such as the gravitational constant, the strength of electromagnetic forces, and the parameters governing the weak and strong nuclear interactions, play critical roles in shaping the dynamics of matter and energy throughout the cosmos. Alterations in these constants can lead to dramatic shifts in the processes that underpin cosmological evolution. For instance, if the gravitational constant were significantly stronger, it would enhance the gravitational attraction between particles. This could lead to rapid clumping of matter, potentially resulting in the formation of stars and galaxies at a much faster rate than we observe in our universe. While this might foster the rapid emergence of larger structures, it could also preclude the development of stable planetary systems, as the forces might be too extreme for delicate balances necessary for planetary orbits. Consequently, complex structures like those conducive to life may never form. Conversely, if the gravitational constant were much weaker, the ability of matter to coalesce into stars and galaxies could be severely hindered. In such a universe, stars might not form effectively, leading to a lack of stable energy sources needed for the synthesis of heavier elements through nuclear fusion. This scarcity of heavier elements would limit the prospects for planet formation and, by extension, the emergence of complex chemistry as it is known on Earth. Similarly, changes to the strength of electromagnetic forces would alter the behavior of atoms and molecules. If electromagnetic interactions were significantly stronger, chemical reactions could occur at such rates that stability becomes disrupted, potentially leading to extremely reactive environments that prohibit the formation of stable compounds. On the other hand, with weaker electromagnetic forces, the bonds forming complex molecules might be too fragile, limiting the diversity of chemistry that is necessary for life. These hypothetical scenarios illustrate how the fine-tuning of physical constants is crucial for the formation of structures that support life and complexity. By exploring how variations in these constants might shape different universes, we glean insights into the delicate balance that underpins our own cosmos and the intricate dance of forces and interactions that lead to the vast, diverse tapestry of existence. Such considerations prompt deeper reflection on not only how life forms, but also the conditions necessary for the emergence of consciousness within the broader context of the universe. The concept of island universes refers to the idea that there may exist distinct regions or pockets of space within a broader multiverse framework where each island operates under its own set of physical laws and constants. This notion envisions a cosmological landscape in which each universe can have localized variations in fundamental forces, particle interactions, and even the structure of space-time itself. These islands, while separate, coexist within a vast and intricate multiverse, leading to an astonishing diversity of cosmic evolutions. In this framework, each island universe could display unique characteristics, resulting in vastly different phenomena. For example, one island universe might have a strong gravitational force that promotes rapid star formation, while another could exhibit weak electromagnetic forces that hinder atomic interactions. These variations might lead to entirely distinct forms of matter, energy distributions, and even different pathways for the evolution of complex structures. The uniqueness of each island supports the idea that the fundamental nature of reality is not monolithic, but instead encompasses a rich tapestry of possibilities. The concept of island universes also aligns with ideas from theories such as string theory and quantum gravity, which postulate that the fundamental laws may arise from underlying configurations at higher dimensional scales. These theories suggest that different regions of space could be influenced by different arrangements of fundamental strings or fields, leading to varied physical realities. Consequently, each island's locally differing physical laws would stem from these unique conditions, emphasizing the fluidity of cosmic parameters and the multiple pathways that evolution could take. Furthermore, the existence of island universes with differing physical laws prompts philosophical questions about the nature of existence and the role of observers within these diverse environments. While we can observe and contemplate our own universe, these island scenarios challenge the limits of our understanding and compel us to wonder about the nature of realities that lie beyond our observational reach. This exploration not only enriches our perception of the cosmos, but also reshapes our inquiry into fundamental questions regarding existence, life, and consciousness in an incomprehensibly diverse multiverse. The number of spatial or temporal dimensions in different universes can vary fundamentally and essentially shape the nature of reality itself. In our own universe, we experience 3 spatial dimensions: length, width, and height, along with a single temporal dimension that we perceive as time. However, various theories in physics suggest that other universes could possess different configurations of dimensions, leading to a wide range of physical laws and phenomena. For instance, string theory postulates that additional spatial dimensions could exist beyond the familiar 3. These extra dimensions might be compactified or curled up in ways that render them imperceptible at human scales, yet they could profoundly affect the behavior of fundamental particles and forces at microscopic levels. If a universe had more than 3 spatial dimensions, it could potentially allow for more complex geometric structures and interactions, fundamentally altering gravity, electromagnetism, and other forces. The implications of these extra dimensions could extend to how matter functions, leading to a radically different landscape of physical reality. In terms of temporal dimensions, the situation is further enriched with possibilities. While we typically think of time as a single continuum, some theoretical frameworks suggest the existence of multiple time dimensions. In a universe with more than one temporal dimension, the flow of time could exhibit drastically different characteristics. One can envision scenarios where events do not follow a linear progression, but rather allow for varied paths through time. This could result in complex causal relationships that defy our conventional understanding, creating a reality where multiple timelines coexist, perhaps influencing events in unknown ways. The configuration of dimensions also impacts the formation of structures and the evolution of matter. For example, a universe with a different number of spatial dimensions might have distinct gravitational behaviors, altering the potential for star formation and planetary systems. Similarly, the presence of more temporal dimensions might challenge the concept of entropy and thermodynamic laws, reshaping our understanding of order and disorder in the cosmos. Ultimately, variations in the number of spatial or temporal dimensions invite us to explore the profound implications for the nature of reality itself. These considerations challenge our traditional views of the cosmos and push us to consider the vast array of possible universes that could exist, each governed by its own set of rules and principles. The exploration of these concepts not only expands our understanding of physical reality, but also fuels our imagination as we contemplate the extraordinary diversity of potential existences in the multiverse. The theory of varying fundamental constants proposes that the fundamental constants of nature, which include values such as the speed of light, the gravitational constant, and the fine structure constant, are not fixed but may change over time or across different regions of the universe. This idea challenges the traditional view that these constants are immutable and universal, leading to intriguing implications for our understanding of physics. In the context of our observable universe, researchers explore how changes in these constants could influence the laws of physics as we understand them. For instance, If the fine structure constant were to vary, it could affect the interactions between charged particles, shaping the formation of atoms, molecules, and ultimately the chemistry that underpins life itself. Such variations could explain certain cosmological observations that do not neatly fit within the standard model of cosmology. Further extending this theory beyond our observable universe opens a realm of fascinating possibilities. If different regions of a larger multiverse possess varying constants, each could host unique physical laws. This would mean that each universe could behave differently, potentially leading to diverse forms of matter and varying levels of structural complexity. The idea that our universe is just one of many, with its own set of constants, raises questions about the very fabric of reality and the nature of existence itself. Ultimately, studying the implications of varying fundamental constants allows scientists to ponder vital questions about the origins of our universe, its ultimate fate, and the underlying principles that govern all of existence. This exploration not only challenges existing theories, but also invites a broader view of the cosmos, where flexibility and variation might be fundamental characteristics of reality. Cosmic wormholes are theoretical passages through space-time that could create shortcuts between distant points in the universe or even connect separate universes entirely. Imagine them as bridges in the fabric of space-time, allowing travel between locations that, if traversed through conventional means, would take an impossibly long time. The concept arises from the equations of general relativity, formulated by Albert Einstein, which suggests that space-time is not just a static backdrop, but a dynamic entity that can be warped and distorted. These wormholes are often described using the framework of Einstein-Rosen bridges, a specific type of wormhole proposed by Einstein and his colleague Nathan Rosen. In their model, two black holes are connected by a tunnel through which matter and information could theoretically pass. This raises the tantalizing possibility that such a connection could link not just different locations within our universe, but might serve as a gateway to entirely different universes, each with its own unique physical laws and constants. Exploring the implications of cosmic wormholes unveils a rich tapestry of scientific speculation. If they exist, overcoming the instability that typically plagues wormholes would be paramount for any form of practical use. Theoretical constructs known as exotic matter, which possesses negative energy density, might be necessary to keep a wormhole open and prevent it from collapsing. This type of matter is still purely theoretical, challenging our understanding of what constitutes the fabric of reality. Imagining wormholes as a means to traverse between distinct universes opens up profound questions about the nature of existence and reality. The idea that our universe might be just one of many connected through these cosmic tunnels not only captivates the imagination, but also invites rigorous scientific inquiry into the fundamental workings of the cosmos. The study of wormholes pushes the boundaries of theoretical physics, suggesting that the universe we see may be just the beginning of a much larger interconnected multiverse. Cosmic strings are hypothetical, one-dimensional topological defects that may have formed during phase transitions in the early universe. These structures are predicted to be incredibly dense and narrow, stretching across vast distances. The idea of cosmic strings arises from advanced theoretical frameworks, including string theory and certain aspects of cosmology, suggesting they could play a transformative role in our understanding of space-time. The connection between cosmic strings and potential gateways between universes is particularly fascinating. When researchers consider the interactions between cosmic strings, it becomes conceivable that these entities could warp the surrounding space-time in such a way that they create pathways or bridges akin to wormholes. This means that if two cosmic strings were to come close enough to each other, their immense gravitational pull could distort space-time enough to form a bridge-like structure, potentially allowing for travel between different regions or even entirely different universes. In some theories, the gravitational effects of cosmic strings could influence the geometry of space-time dramatically. The unique properties of these strings might lead to scenarios where so-called string loops or interactions between multiple strings give birth to new space-time configurations that allow the traversal of dimensions. Such pathways could serve as gateways to alternate realities within the framework of a multiverse scenario, where each universe possesses its own distinct physical characteristics. While these ideas remain largely within the realm of speculation, investigating cosmic strings adds an exciting layer to both cosmology and theoretical physics. Understanding how such objects might behave and interact not only provides insight into fundamental questions about the universe, but also fuels the imagination about how different realities might be interconnected through exotic structures like cosmic strings. This exploration highlights the ongoing quest to decipher the profound mysteries of the cosmos, bringing us closer to grasping the complexities and potential diversities of existence itself. So, domain walls are theoretical two-dimensional defects in the fabric of space-time that can arise during phase transitions in the early universe. Just as a bubble forms when water boils, these walls can form when different regions of the universe settle into distinct states with differing vacuum energy densities. In cosmological terms, the universe could evolve into multiple states or phases, each with unique physical properties. The boundaries between these different states are referred to as domain walls. When we contemplate the implications of domain walls, their role becomes intriguing, especially regarding the idea of separating different universes within a multiverse perspective. If the universe underwent a phase transition that resulted in the creation of multiple distinct vacuum states, these domain walls could serve as the interfaces delineating those states. Essentially, they could act as barriers that define regions with varying physical laws, constants, or even dimensions, possibly leading to entirely different realities nestled within the broader multiverse. The properties of these domain walls might lead to fascinating consequences. For instance, if two vacuum states possess different laws of physics, then crossing through a domain wall could mean entering an environment where the fundamental forces behave in novel ways. This means that not only could domain walls separate different universes, but they could also facilitate interactions between them, potentially allowing for the exchange of energy, particles, or information, depending on their specific properties. The study of domain walls is still largely theoretical, with ongoing research exploring their potential formation, stability, and implications for cosmic evolution. Understanding these defects adds a compelling layer to cosmology, inviting contemplation on how the universe as we know it might be just one of many interconnected realms. The existence of domain walls sparks curiosity about the nature of our universe and the myriad possibilities that may lie beyond our perceptible reality. Quantum entanglement is a remarkable phenomenon in quantum mechanics where two particles become interconnected in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. This intriguing relationship challenges our classical intuitions about locality and separateness, suggesting that information can be shared in ways that transcend traditional physical boundaries. As scientists delve deeper into the implications of entanglement, they begin to explore its potential role in bridging parallel universes. Shown. In the framework of the multiverse hypothesis, where multiple universes exist parallel to our own, quantum entanglement may offer a mechanism for interconnections. Each universe could represent a distinct outcome of quantum measurements, with entangled particles creating a web of correlations between events across these different realities. For instance, if particles are entangled through interactions in one universe, their corresponding counterparts could be affected in another universe, creating a tapestry of intertwining states across the multiverse. This idea resonates with interpretations of quantum mechanics, such as the many worlds interpretation. In this view, every quantum event leads to the branching of the universe into multiple paths, each corresponding to a different outcome. If entangled particles exist across these branches, they might share information or states, effectively linking the parallel realities. Such connections could provide a fascinating insight into how events in one universe might influence or correlate with events in another. Although the notion of quantum entanglement bridging parallel universes remains speculative and theoretical, it inspires rich discussions about the nature of reality and the fundamental workings of the universe. It raises critical questions about how we understand causality, interaction, and the very fabric of existence. As researchers continue to explore the implications of entanglement, they delve into a complex and captivating realm where the boundaries of universes blur, hinting at an interconnectedness beyond our current comprehension. The concept of brane collisions emerges from string theory, where our universe is envisioned as a three-dimensional object known as a brane, short for membrane, that exists within a higher dimensional space. In this framework, multiple branes can exist simultaneously, and interactions between these branes could lead to significant events, such as collisions. These interactions are not just theoretical curiosities, they might play a fundamental role in shaping the physical characteristics of our universe and others. When two branes collide, the energy released from this dramatic interaction could initiate a variety of cosmic phenomena. For instance, such a collision might create new regions of space-time and potentially trigger the birth of new universes. This aligns with certain cosmological models suggesting that our universe may have originated from a brane collision, marking the moment of the Big Bang. The consequences of these collisions could not only generate matter and energy, but also set the stage for unique physical laws and constants in the resulting universes. The interfaces formed by brane collisions could serve as boundaries between distinct realms within the multiverse. Each brane might represent a universe with its own set of properties and laws. As such, these interfaces could function as transitional areas, where the phenomena from one universe interact with those from another. This interaction could facilitate the exchange of information, particles, and even energy, leading to a complex web of connected realities. Exploring the dynamics of brane collisions invites profound questions about existence and the nature of the cosmos. These interactions highlight the idea that our universe may not be isolated, but could be part of a grander multiverse, enriched by the presence of neighboring branes. The study of branes and their collisions expands our understanding of fundamental physics while encouraging us to think about the vast possibilities that may lie beyond our observable universe. Closed time-like curves are fascinating theoretical constructs in the realm of general relativity that allow for the possibility of time travel. A closed time-like curve is a path through space-time that loops back on itself, meaning that an object following such a curve could return to its own past. This concept poses intriguing questions about causality and the nature of time itself, leading to rich discussions about its implications for connections between universes. In the context of a multiverse scenario, closed time-like curves may create pathways that link different universes or timelines. The existence of such curves could enable travel not just within the temporal fabric of a single universe, but also across various parallel realities. For example, if a closed time-like curve arises at the intersection of multiple universes, it might allow for a traveler to enter one universe at a certain time and exit in another universe at a different time, connecting disparate realities in a way that challenges our understanding of linear causality. The scenario of closed time-like curves introduces paradoxes that complicate traditional notions of time and sequence. For instance, the famous grandfather paradox questions what would happen if someone traveled back in time and inadvertently prevented their own existence. These complexities lead theorists to ponder whether the multiverse could provide a resolution. In this framework, actions taken in one universe might create alternate branches that diverge from the original timeline, thereby allowing time travel without collapsing a singular, consistent history. While closed time-like curves remain speculative and their practical implementation is theoretical, exploring their implications enriches the discourse on the very nature of reality. This inquiry encourages deep contemplation about how time, causality, and parallel universes might intertwine in a way that defies conventional reasoning. The study of such curves continues to inspire physicists and philosophers alike, inviting them to engage with the complexities and wonders of the cosmos. The idea of bubble collisions arises from the theory of eternal inflation, which posits that the universe underwent a rapid exponential expansion in its early moments. In this framework, different regions of space can stop inflating at different times, leading to the formation of bubbles of space where inflation has ceased. Each bubble can have its own unique physical properties, possibly resulting in diverse universes within the broader multiverse. When two of these bubbles collide, the event is known as a bubble collision. The consequences of such collisions can be quite dramatic, potentially creating new forms of matter, energy, or even entirely new regions of space-time. In an eternal inflation scenario, a bubble collision provides a fascinating mechanism that could connect different universes. As the bubbles are formed from vast regions of inflating space, their interactions might unify their physical characteristics or offer an avenue for energy exchange, establishing a link between the seemingly separate realms. The implications of bubble collisions stretch into the realm of theoretical physics, where they invite speculations about the nature of our universe and others. For instance, if our universe is a bubble that formed during this period of inflation, a collision with another bubble could explain certain irregularities in the cosmic microwave background radiation or other cosmological phenomena. Each universe's unique bubble may reflect different initial conditions or physical laws arising from the inflationary process, creating a diverse landscape of realities where the properties of one could influence another. Furthermore, bubble collisions raise intriguing questions about the overall structure of the multiverse. They suggest a dynamic interconnectivity, providing a richer understanding of how separate universes might interact. Through this lens, the very fabric of reality becomes a complex interplay, characterized by the potential for diverse universes to collide, share properties, and evolve independently, while still maintaining connections through these dramatic encounters. This exploration encourages an ongoing investigation into the nature of emergence, symmetry, and diversity within the cosmos, reshaping the way we perceive existence itself. Higher dimensions are a compelling aspect of theoretical physics, especially in frameworks like string theory and brane world scenarios. These theories suggest that, in addition to the familiar three dimensions of space and one of time, there could exist additional spatial dimensions that are either compactified or otherwise not easily observable. The existence of these higher dimensions raises intriguing possibilities regarding how they might function as conduits between different universes. In the context of multiverse theories, higher dimensions could act as the underlying structure through which distinct universes interact. Imagine our universe as a three-dimensional brane embedded within a higher dimensional space. This higher dimensional arena could contain multiple branes, each representing a separate universe with its own unique physical laws and constants. In this view, the excess dimensions provide a medium for events or interactions that transcend the limitations of our familiar three-dimensional experience. When considering the dynamics of these higher dimensions, a number of intriguing scenarios arise. For instance, if two branes were to collide within this higher dimensional space, the interaction might generate a ripple effect that influences the configurations of both universes. Moreover, the geometry of the higher dimensional space could permit shortcuts, akin to wormholes, connecting different branes. This arrangement suggests that higher dimensions might facilitate pathways for particles, energy, or information to traverse from one universe to another, potentially leading to inter-universal interactions. Additionally, higher dimensions could offer insights into the fundamental nature of reality, allowing for phenomena that seem impossible within the constraints of our usual experiences. By framing the interactions between universes in higher dimensional terms, we may better understand the underlying principles governing the multiverse and how it manifests in various forms. This exploration not only broadens our understanding of physics, but also ignites discussions about the very fabric of existence and the interconnectedness of realities that may lie beyond our current perceptual boundaries. The concept of quantum tunneling between universes arises from the principles of quantum mechanics, particularly the phenomenon known as quantum tunneling. This refers to the ability of particles to pass through potential energy barriers, even when they seemingly lack the energy to do so. The particle is not confined to classical paths dictated by its energy. Rather, it has a probability of appearing on the other side of the barrier, leading to surprising outcomes in a variety of quantum processes. Extending this idea to the realm of multiple universes proposes that quantum tunneling could facilitate connections or transitions between different universes. In a multiverse framework, if our universe represents one of many possible configurations, quantum tunneling might allow certain particles or information to traverse the boundary between universes. This could happen if a particle finds itself at the threshold of a potential barrier that isolates one universe from another. The tunneling effects could enable access to alternate realities that would otherwise be unreachable through classical means. The mathematical foundation for this notion rests on the wave nature of particles, where each potential state exists as a probability wave. If we consider a separation between two universes as a type of barrier, quantum tunneling would imply that there exists a non-zero probability for certain particles to cross over into the adjacent universe. Such transitions might not be routinely observable on macroscopic scales, but could manifest in specific quantum events or at extremely small lengths, affecting the distribution of particles or energy. While this idea is still highly speculative and primarily theoretical, it provides a captivating lens through which to contemplate the nature of reality, causality, and the underlying structure of the multiverse. Quantum tunneling suggests that rather than being entirely distinct and isolated, our universe might be connected to others through subtle, probabilistic pathways, creating a more intricate tapestry of existence. This exploration invites scientists and thinkers alike to consider the vast possibilities that arise when we expand our understanding of quantum mechanics and its implications for the cosmos. The holographic principle is a fascinating concept emerging from theoretical physics, particularly in the context of black hole thermodynamics and string theory. It posits that all the information contained within a volume of space can be represented as a two-dimensional surface that encloses that space. This implies that our three-dimensional reality may be an expression of information encoded on a distant, lower-dimensional boundary, much like a hologram produces three-dimensional images from two-dimensional data. In consideration of potential connections between universes, the holographic principle suggests that there could be a deeper interconnectedness among multiple realities. If each universe within a multiverse can be viewed as a projection from a higher dimensional surface, then it stands to reason that the boundaries defining these universes might carry important information about their relationships. Such boundaries could serve as platforms for the exchange of information or energy, implying that what happens in one universe could have implications for another situated within the same higher dimensional framework. This notion resonates with the idea that the properties of one universe could be influenced by its neighboring universes, as the encoded information at the boundary could encapsulate the dynamics and interactions of multiple universes. For example, if two universes share aspects of their holographic boundaries, their physical laws might be subtly interlinked, leading to interactions that could manifest as observable effects in one or both of the realms. Such a framework suggests a unity underlying the apparent diversity of universes, where differences may stem from variations in how higher dimensional information is expressed. Moreover, the holographic principle raises intriguing inquiries about space-time itself, inviting us to rethink fundamental concepts like locality and causality. In this light, the boundaries of existence might not solely define separateness, but could act as conduits through which universes interact. The exploration of the holographic principle continues to inspire profound discussions on the nature of reality and our understanding of the cosmos, revealing the tantalizing possibility that a deeper, interconnected fabric underlies the multitude of universes we can imagine. The cosmic microwave background radiation, often called the CMB, is the afterglow of the Big Bang and provides a wealth of information about the early universe and its subsequent evolution. Scientists have speculated that certain anomalies within the CMB could serve as signatures of other universes or interactions with them, indicating that we might not be entirely alone in the cosmos, but part of a more complex multiverse landscape. One potential signature of other universes could manifest as unusual temperature fluctuations or patterns in the CMB. For instance, if our universe had undergone a collision with another bubble universe during eternal inflation, remnants of that interaction might show up as specific anisotropies in the CMB. Researchers look for alignment or configurations that deviate from the expected Gaussian distribution of temperature variations. Unidentified cold or warm spots could suggest regions influenced by the gravitational effects of another universe or the remnants of bubble collisions. Another intriguing possibility involves the existence of cosmic string signatures. If cosmic strings, hypothetical one-dimensional defects in spacetime, exist, they could create unique distortions in the CMB. As these strings have high mass and density, they could affect the path of photons traveling through the universe, resulting in certain identifiable patterns or gravitational lensing effects detectable in the CMB. Evidence of such phenomena could suggest even further complexities in the universe's fabric and possibly hint at connections to other realities. Additionally, primordial gravitational waves generated by events like inflation could leave imprints on the CMB polarization patterns. These imprints might also be influenced by interactions with other universes, pointing toward the presence of additional cosmic dynamics beyond our observable horizon. Identifying these subtle features requires precise measurements and analysis, and scientists are continually refining their instruments and methods to probe deeper into the CMB data. While the evidence for other universes remains theoretical at this point, the CMB serves as a critical observational tool that could potentially unveil clues about the broader multiverse context in which our universe exists. Ongoing explorations of the CMB are central to understanding not only the origins of our cosmos, but also the tantalizing prospect of what may lie beyond our immediate reality. Gravitational waves, ripples in spacetime produced by some of the most energetic processes in the universe, offer a unique window into understanding cosmic events and potentially accessing evidence for universes beyond our own. Detected for the first time in 2015 by the LIGO Observatory, these waves are generated by phenomena such as the mergers of black holes or neutron stars. As the study of gravitational waves advances, researchers are beginning to hypothesize ways in which these phenomena could hint at the existence of a broader multiverse. One avenue of exploration involves the possibility that events leading to gravitational wave emissions could be influenced by structures or interactions with other universes. For instance, if two black holes were to collide as a result of a bubble collision between two inflating universes, this might leave a distinctive signature in the gravitational waves produced during the merger. The resulting characteristics of these waves, such as their frequencies or amplitudes, could reveal anomalies that suggest an underlying connection to another universe's dynamics. Moreover, gravitational waves carry information that transcends standard matter interactions. They are not hindered by material obstacles, allowing them to travel vast distances without being absorbed or scattered. This means that gravitational waves from particularly violent events involving multiple universes might provide unique insights into the energy scales and properties of those realities. If such waves originated from a collision of branes or interactions between bubble universes, their detection could suggest the existence of these alternate realms and their features. Additionally, the study of gravitational wave backgrounds, an almost constant hum of mergers from various far-off events, might uncover a rich tapestry of cosmic activity. Fluctuations or anomalies in this background spectrum could imply interactions with external universes, particularly if there are correlations between the events observed through gravitational waves and those recorded through traditional electromagnetic channels. Researchers continue to investigate these possibilities, making connections across disciplinary boundaries to understand what this complex data could imply about our existence in a multiversal framework. As the sensitivity of gravitational wave observatories improves, the potential to discern these subtle signals increases. The nature of gravitational waves makes them a promising avenue for exploring the fundamental composition of our cosmos, possibly revealing links to other realities that deepen our understanding of the universe's ultimate nature. This exploration invites us to consider profound questions about reality, existence, and the vast unknowns that may lie beyond our own universe. The concept of cosmic bruises refers to specific features in the cosmic microwave background radiation that could serve as evidence of past collisions between our universe and other universes. These bruises may manifest as unusual anomalies, such as temperature fluctuations or patterns that deviate from the expected uniformity of the CMB. They are derived from the idea that if two universes were to collide, the energetic interaction could leave a distinct imprint on the fabric of space-time, an imprint that might be observable as variations in the CMB. When considering the notion of cosmic bruises, researchers look for localized areas within the cosmic microwave background that appear different from the surrounding regions. These spots might indicate where another universe's bubble has collided with our universe's bubble during the inflationary phase of cosmic expansion. Such gravitational interactions could generate waves and energies that perturb the CMB, leading to detectable variations in temperature or polarization that hint at the presence of another universe and the energetic effects of the collision. For example, if a bubble universe collides with our own, the resulting disturbance could create a large-scale memory of that encounter in the CMB's structure. As researchers analyze the intricate data captured by observatories studying the CMB, they are on the lookout for patterns such as unusual cold or hot spots that could suggest these types of interactions. Identifying these cosmic bruises would provide compelling evidence for the theory of eternal inflation and the existence of a multiverse. As scientists continue to explore and analyze cosmic data, they are equipped with increasingly sophisticated tools and technologies that enhance their ability to detect subtle features of the primordial radiation. Cosmic bruises may hold the key to understanding not only our universe's history, but also the broader context of existence itself, revealing the potential effects of interactions with other universes in a complex multiverse landscape. This pursuit continues to captivate researchers, beckoning them to uncover secrets about the interconnectedness of realities beyond our immediate observations. Future advances in quantum measurements hold the potential to provide significant insights into the existence of parallel universes, particularly through their ability to probe the fundamental nature of quantum mechanics. As scientists develop more sensitive and precise measurement techniques, they may uncover phenomena that hint at the existence of multiple realities simultaneously existing alongside our own. One key area of exploration is the realm of quantum superposition, where particles can exist in multiple states until measured. Traditional interpretations of quantum mechanics suggest that measuring a particle collapses it into one state, while other interpretations, such as the many worlds interpretation, propose that all possible outcomes occur, each corresponding to a different universe. As measurement technologies improve, scientists may be able to perform experiments that explore the boundaries of superposition in unprecedented detail, potentially revealing signs of parallel universes through the observation of outcomes that hint at branching realities. Another avenue involves the study of entanglement and its implications for interconnectedness between quantum systems. Enhanced measurement techniques could allow researchers to investigate correlations between entangled particles at greater distances or under more complex configurations. Observing unexpected correlations or effects that cannot be explained by conventional models could suggest the influence of other universes interacting with our own. Such findings might provide a concrete basis for the existence of parallel realities that affect quantum outcomes in ways not yet fully understood. Moreover, advances in quantum computing might facilitate simulations of quantum systems that more accurately reflect potential multiversal behavior. By modeling complex interactions and exploring how quantum states might correlate across different branches of reality, researchers could glean insights into how these universes might interact. If experimental results align with the predictions of these models, it could serve as indirect evidence for the existence of parallel universes. Ultimately, as quantum measurement techniques continue to evolve, they could illuminate the fascinating interplay between reality and the underlying principles of quantum mechanics. By unraveling the complexities of quantum behavior, scientists might not only enhance our understanding of the universe, but also provide compelling evidence for the existence of parallel universes, offering a tantalizing glimpse into a reality far richer than we presently perceive. Neutrino astronomy holds immense potential in the quest to understand phenomena beyond our own universe, including the intriguing idea of parallel or alternate universes. Neutrinos are subatomic particles that are incredibly light and neutral, allowing them to pass through ordinary matter almost unhindered. This property makes them excellent messengers from distant cosmic events, even those that might not be observable through traditional telescopes. As we explore the cosmos, neutrinos could help detect signs of other universes by revealing unique interactions that occur during cosmic events, such as supernovae or the collision of black holes. For instance, if there are interactions occurring between our universe and another, neutrinos might carry evidence of these interactions back to Earth. The patterns and energies of these neutrinos could reveal anomalies that suggest influences from other universes, hinting at phenomena that standard models of physics cannot explain. Additionally, certain theories, like string theory, propose multiple dimensions or parallel universes. Neutrinos might be sensitive to these extra dimensions, as their behavior could be altered in ways that differ from our typical understanding of particle physics. By studying their trajectories, energies, and interactions, scientists could potentially uncover clues pointing to the existence of other universes intertwined with our own. The study of neutrinos is still in its early stages, but as technology advances, so does our ability to create larger and more sensitive detectors spread across the globe. These developments could lead to groundbreaking discoveries. If neutrino astronomy reveals unexpected results, it may open new pathways in the exploration of multiverse theories, changing the way we perceive our place in the cosmos. Cosmic voids, those vast and seemingly empty spaces between the filaments of galaxies, are integral to understanding the large-scale structure of the universe. Although they appear to be devoid of matter, studying these voids can reveal significant insights about the cosmos, including regions beyond our observable universe. Their very existence challenges our understanding of gravity and cosmic evolution, making them a focal point for astrophysicists. These voids are not just empty, they have unique properties that reflect the gravitational influences of surrounding structures. As researchers analyze the distribution and size of voids, patterns may emerge that suggest how matter is arranged in the universe. Such patterns can provide clues regarding the distribution of dark energy and dark matter, which together influence the expansion of the universe. By understanding these voids, scientists can infer how the universe's fabric behaves beyond the limits of what we can observe. Moreover, cosmic voids can act as a sort of lens, allowing researchers to study light from distant celestial bodies behind them. This phenomenon, known as gravitational lensing, can amplify light and enable the observation of galaxies and structures that would otherwise remain hidden. If there are cosmic regions beyond our observable universe, voids might allow us to glimpse some of the light and gravitational effects coming from them, hinting at the existence of unobserved structures. Astrophysicists also theorize that the nature of cosmic voids may differ significantly in various regions of the universe, potentially informed by the cosmic inflation theory. Such differences could signal interactions with parts of the universe that remain beyond our reach. As we gather more data on the characteristics and distributions of voids through advanced astronomical surveys, these findings might ultimately provide the insights needed to connect our universe with those elusive regions beyond our observable limits. The concept of anomalous cold spots in the cosmic microwave background radiation, often abbreviated as CMB, refers to areas within this afterglow of the Big Bang where the temperature is notably lower than the average background temperature. The CMB itself is a relic from when the universe was just about 300,000 years old, providing a wealth of information about the early universe, including its composition and the conditions that led to the structure we observe today. These cold spots stand out because they are regions that appear unusually empty or less dense compared to their surroundings. One of the more intriguing theories regarding these cold spots is that they could represent the remnants of cosmic events or influences outside of our observable universe. Some researchers speculate that these anomalies might be the result of interactions with other universes. For example, if our universe collided with another universe, it could leave behind a distinct signature in the CMB, manifesting as these unique cold spots. This idea aligns with certain multiverse theories, suggesting that realities beyond our own may be influencing the cosmic background we observe. While most traditional explanations for these cold spots involve cosmic structures or effects arising within our own universe, the notion of them pointing to interactions with other universes offers a tantalizing possibility. If confirmed, these cold spots could indicate that our universe is not isolated, but rather part of a larger multiverse where various cosmic realities coexist and interact in ways we are only beginning to comprehend. As scientists continue to analyze data from CMB observations, particularly from instruments like the Planck satellite, the quest to understand these anomalous cold spots may provide crucial clues about the fundamental nature of reality. This research might not only enhance our understanding of the early universe, but also spark new discussions about the potential existence of other universes and how they might coexist with or influence our own. Future space-based gravitational wave detectors, such as the proposed laser interferometer space antenna, hold extraordinary promise for deepening our understanding of the universe, including the tantalizing possibility of signs of other universes. Gravitational waves are ripples in space-time, produced by some of the most powerful events in the cosmos, such as the merging of black holes or neutron stars. By detecting these phenomena, scientists can gain insight into the fundamental laws of physics, but there is also potential for identifying characteristics that point to alternate realities. One area of interest is how gravitational waves might behave differently if they interacted with other dimensions or universes. Current theories in high-energy physics, including those related to string theory, suggest that our universe might coexist with others in a higher dimensional space. If this is the case, gravitational waves that originate from events in our universe could carry additional information about the properties of these extra dimensions. Anomalies in wave behavior, frequency, or propagation could hint at influences from other universes, providing a unique observational avenue for probing questions about the multiverse. Moreover, gravitational wave detectors can examine the collision of objects at extreme energies and densities. If there were interactions between our universe and another, such gravitational events could potentially create waves with unique signatures that differ from what typical astrophysical events would produce. Analyzing these signals allows scientists to search for specific patterns that may suggest inter-universal interactions or the collision of other dimensional objects. As technology evolves and we develop more sophisticated space-based gravitational wave observatories, we will enhance our ability to detect these elusive waves and refine our interpretation of the data they provide. The exploration of gravitational waves is a frontier discipline that offers the chance to not only deepen our understanding of the cosmos, but to possibly uncover evidence of the extraordinary tapestry that might include multiple universes. Each discovery may lead us closer to answering profound questions about the nature of reality beyond our observable horizons. The study of dark energy is pivotal in cosmology, as it constitutes approximately 70% of the universe's total energy content and is responsible for the accelerated expansion of the universe. Understanding dark energy not only shapes our knowledge of the cosmos, but could also provide insights into the existence of other universes. The behavior and properties of dark energy might hint at mechanisms or interactions that transcend our understanding of a single universe. Currently, dark energy is largely a mystery, with its fundamental nature still unknown. Several theories propose that it could be a manifestation of a cosmological constant, a dynamic field known as quintessence, or even an effect stemming from extra dimensions as suggested by some theories in physics. If dark energy is connected to higher dimensions or different types of energy fields existing alongside our universe, this could imply that our universe is influenced by or linked to other realities. Researchers are also investigating the effects of dark energy on large-scale cosmic structures. Anomalies in the distribution and evolution of galaxies may provide clues to understanding dark energy's role, and if these anomalies do not align with predictions based on observable physics, they may suggest interactions with other universes. For example, if dark energy behaves differently over vast distances or in certain regions of space, this could indicate influences from alternate realities that manifest through gravitational effects or alterations in the expansion rate of the universe. Future observations and experiments aimed at probing dark energy, including surveys of galaxy distributions and cosmic microwave background measurements, could unveil hidden details about its properties. Discoveries that challenge established models might pave the way for multiverse considerations, altering our existing theories about the universe's expansion. Ultimately, the ongoing study of dark energy could play a critical role not only in deciphering the mysterious forces driving our universe's evolution, but also in exploring the potential existence of other universes intertwined with our own in ways we are just beginning to imagine. Advancements in the detection of dark matter particles could significantly enhance our understanding of the universe, illuminating potential connections to realms beyond our own. Dark matter, which makes up about 27% of the cosmos, does not emit or absorb light, making it challenging to detect. However, scientists are striving to uncover the properties of dark matter particles using advanced technologies and methods, including underground detectors and large particle colliders. One hypothesis is that dark matter could be a manifestation of particles that interact with gravity and other forces in unforeseen ways. If researchers succeed in identifying and directly detecting these particles, it might indicate that dark matter does not exist solely within our universe, but may also have ties to other universes. For example, certain theories suggest that dark matter might leak into our universe from adjacent dimensions or alternate realities, potentially altering the behavior of gravitational fields we observe. Furthermore, if dark matter particles exhibit behaviors or properties that deviate from standard physics predictions, this would suggest interactions with extra dimensions or other universes. For instance, additional forces or interactions could alter how dark matter particles are distributed across space, providing indirect evidence for the influence of different realms. As technologies advance, focusing on more sensitive detectors and novel experimental techniques, the goal is to uncover the elusive nature of dark matter. Discoveries regarding dark matter could ripple across our understanding of fundamental forces, providing theoretical underpinnings that not only explain the cosmos, but also hint at the existence of multiple universes. Each new finding about dark matter has the potential to reshape our comprehension of both the immediate universe and the broader multiverse, encouraging further exploration of the connections that might lie beyond our observable reality. The concept of a living cosmos pushes the boundaries of our understanding of life and consciousness. In this view, the universe or multiverse might possess qualities we typically associate with living systems, but on a scale and complexity far beyond our current comprehension. This cosmic vitality could manifest in the form of vast energy flows, self-regulating processes, and the capacity for growth and adaptation. Imagine a multiverse where each universe is like a neuron in a cosmic brain, with quantum entanglement serving as synapses connecting these universal nodes. Information and energy might flow through these connections, creating patterns of activity that could be interpreted as thoughts or decisions on a cosmic scale. This living cosmos might exhibit behaviors analogous to cognition, with different regions of the multiverse specializing in various cognitive functions. Some areas might focus on memory storage, preserving information about past universal configurations. Others could act as processing centers, where complex calculations regarding the evolution of physical laws take place. The overall structure could even possess a form of cosmic consciousness, with the collective behavior of countless universes giving rise to a self-aware entity of unimaginable complexity. The reproduction of universes in this living cosmos could occur through various mechanisms, each with its own fascinating implications. The idea of universes splitting or budding off from parent universes suggests a form of cosmic mitosis. This process might be triggered by specific conditions within a universe, such as the density of dark energy reaching a critical threshold, or the formation of specialized structures that act as cosmic reproductive organs. As a universe expands and evolves, it might develop regions with unique properties that eventually separate and form new independent universes. Another intriguing possibility is that black holes serve as cosmic wombs, nurturing the development of new universes. In this scenario, the extreme conditions at the heart of a black hole could cause a localized Big Bang, giving birth to a new universe with its own spacetime. This new universe would be connected to its parent universe through the black hole, perhaps allowing for a transfer of information or energy between the two. Over time, a complex network of interconnected universes could form, linked by a web of black hole umbilical cords. The concept of cosmic natural selection takes inspiration from biological evolution and applies it to the multiverse. In this framework, universes with properties that favor the creation of black holes or other universe-spawning phenomena would be more likely to produce offspring universes. These daughter universes would inherit some characteristics from their parents, but with slight variations. Cosmic mutations, if you will. Over time, this process could lead to the evolution of universes with increasingly complex and stable properties. This cosmic evolutionary process might explain the apparent fine-tuning of our own universe. Rather than being the result of intelligent design or pure chance, the physical laws and constants that allow for the existence of complex structures and life could be the outcome of countless iterations of universal reproduction and selection. Our universe, with its ability to form stable atoms, stars, and galaxies, might be the product of a long lineage of increasingly refined universal ancestors. The evolution of universes over time presents a fascinating area for speculation. Unlike biological evolution, which is constrained by the laws of physics in our universe, cosmic evolution could involve changes to the fundamental fabric of reality itself. As universes age, they might develop new properties or capabilities, such as the ability to support more complex forms of matter or energy. This could lead to the emergence of entirely new physical phenomena, unobservable and perhaps unimaginable from within our own universe. Cosmic evolution might also involve periods of rapid change, analogous to evolutionary punctuated equilibrium. These cosmic revolutions could be triggered by interactions between universes, the influence of higher dimensional spaces, or the emergence of new fundamental forces. During these periods of accelerated change, new types of universes might suddenly appear, with radically different properties from their predecessors. These novel cosmic forms could then undergo their own evolutionary processes, potentially leading to an ever-increasing diversity of universal types. The concept of universe metabolism suggests a complex system of energy and information exchange between universes. This cosmic metabolism could involve the transfer of fundamental particles, fields, or even abstract quantities like information or entropy. In this vast cosmic economy, the waste products of one universe might serve as vital resources for another, creating intricate webs of interdependence across the multiverse. For example, a universe nearing the end of its life cycle, approaching heat death or a big crunch, might release enormous amounts of energy or information. This cosmic exhaust could then be captured by younger, growing universes, fueling their expansion or increasing their complexity. Some universes might specialize in energy production, acting as cosmic power plants that supply neighboring universes with the fuel they need to maintain their physical laws and structures. Other universes might focus on information processing, serving as cosmic computers that solve complex problems or store vast amounts of data. These information-centric universes could act as the memory banks or processing centers of the larger multiverse, perhaps playing a crucial role in the evolution and self-regulation of the cosmic whole. The idea of symbiosis between universes opens up fascinating possibilities for cosmic ecology. Just as organisms in an ecosystem develop complex relationships, universes in a multiverse might form intricate networks of mutual dependence and benefit. Some universes might act as cosmic incubators, providing ideal conditions for the formation and growth of baby universes. These nursery universes could have physical laws fine-tuned for the rapid development of new cosmic structures, serving as spawning grounds for the next generation of universes. Other universes might play a stabilizing role, helping to maintain the overall structure of the multiverse. These cosmic anchors could have extremely stable physical laws that resist change, providing a framework around which more dynamic universes can form and evolve. The interaction between stable and dynamic universes might create a balance that allows for both consistency and innovation in the broader multiverse. Some universes might form symbiotic pairs or groups, each providing something essential for the others. For instance, one universe might excel at producing complex matter, while another specializes in generating exotic forms of energy. Together, these universes could achieve levels of complexity and stability that neither could reach alone. Over time, these symbiotic relationships could lead to the emergence of universe clusters or superorganisms composed of multiple interconnected universes, each playing a specialized role in the larger entity. The concept of cosmic immune systems suggests that universes might develop mechanisms to protect themselves from various threats. These threats could include collapse due to internal instabilities, intrusion from other universes, or degradation of fundamental physical laws. Universes with robust immune systems would be more likely to survive and reproduce in the larger multiverse, leading to the evolution of increasingly resilient cosmic forms. These protective mechanisms might include the ability to repair tears in space-time, perhaps through the generation of exotic matter with negative energy density. Universes might also develop ways to neutralize potentially destructive fluctuations in vacuum energy, maintaining a delicate balance that prevents both rapid expansion and collapse. More advanced cosmic immune systems might even be able to repel invasive forms of matter or energy from other universes, maintaining the integrity of their own physical laws and structures. Over time, universes might evolve increasingly sophisticated defense mechanisms, leading to a kind of cosmic arms race between different universal forms. Some universes might develop offensive capabilities, attempting to expand into neighboring cosmic territory or siphon resources from other universes. In response, defensive capabilities would need to evolve, potentially leading to the emergence of highly secure fortress universes that are extremely resistant to external influences. The idea of cosmic ecological niches suggests that different types of universes might specialize in various roles within the larger multiverse structure. This specialization could lead to a rich tapestry of universal types, each adapted to specific functions or environments. For instance, some universes might be optimized for the production of black holes, serving as cosmic engines that drive the creation of new universes. These black hole factories might have physical laws that favor the rapid formation and growth of massive stars, leading to frequent supernova explosions and the creation of numerous black holes. Other universes might specialize in supporting diverse forms of life, acting as cosmic biodiversity hotspots. These life-friendly universes could have physical constants fine-tuned to allow for the formation of complex organic molecules and stable planetary systems. Within these universes, a vast array of life forms might evolve, potentially including types of life radically different from what we observe on Earth. Some universes might excel at information processing, effectively serving as cosmic computers. These computation-centric universes could have physical laws that allow for the efficient manipulation and storage of information, perhaps utilizing quantum effects on a grand scale. Such universes might play a crucial role in solving complex problems that affect the entire multiverse, or in preserving knowledge from dying universes. Energy-producing universes could serve as power sources for the cosmic ecosystem. These universes might be characterized by high levels of vacuum energy or frequent high-energy events like gamma-ray bursts. The excess energy generated by these universes could be tapped by neighboring cosmic regions, fueling various processes across the multiverse. The interaction between these specialized universes could drive the overall evolution and complexity of the multiverse. Energy from power-generating universes might fuel the computational processes in information-centric universes. The results of these computations could then influence the development of life-bearing universes, creating a complex web of cause and effect that spans the entire cosmic ecosystem. The importance of cosmic biodiversity in a multiverse scenario cannot be overstated. Just as biodiversity on Earth contributes to the resilience and adaptability of ecosystems, cosmic biodiversity could ensure the long-term survival and evolution of the multiverse as a whole. A diverse range of universe types, each with unique properties and capabilities, would make the multiverse more resilient to large-scale disturbances or changes. This diversity might manifest in countless ways. Some universes might have different numbers of spatial or temporal dimensions, leading to physics and structures utterly alien to our understanding. Others might operate under entirely different sets of physical laws, perhaps lacking concepts like electromagnetism or strong nuclear force, but possessing other fundamental interactions unknown in our universe. The interplay between these diverse cosmic forms could drive innovation and complexity at the grandest scales. Ideas, in the form of successful physical laws or universal structures, might be shared between compatible universes, leading to a kind of cosmic cross-pollination. This exchange could accelerate the evolution of the multiverse, allowing for the rapid spread of beneficial traits across vast cosmic distances. Moreover, cosmic biodiversity could serve as a safeguard against existential threats to the multiverse. If some catastrophic event were to endanger a particular type of universe, the existence of diverse alternative forms would ensure that the multiverse as a whole could survive and continue to evolve. This resilience might be crucial in the face of theoretical threats like vacuum decay or the collision of brains in some models of string theory. The application of adaptation and fitness principles to universes in a larger cosmic ecosystem presents mind-boggling possibilities. The concept of fitness at a universal scale might involve factors we can barely conceive, such as a universe's ability to support the emergence of consciousness, its capacity to store and process information, or its resilience in the face of cosmic catastrophes. Universes that are better fit, perhaps those that can sustain complexity, produce black holes, or maintain stable physical laws, might be more likely to spawn new universes or persist over longer cosmic timescales. This cosmic fitness landscape could drive the evolution of universes towards increasingly stable and complex forms. However, the nature of this evolution might be very different from biological evolution as we understand it. For instance, the timeframes involved in cosmic evolution could be inconceivably vast, with significant changes occurring over billions or trillions of years. The mechanisms of inheritance and mutation might operate on the level of fundamental physical constants or the fabric of space-time itself. Selection pressures could come from interactions with other universes, the influence of higher dimensional spaces, or even the conscious intervention of advanced cosmic civilizations capable of universe engineering. As universes compete and adapt within this vast cosmic arena, the multiverse itself might evolve towards greater levels of complexity and order. This could lead to the emergence of cosmic structures or phenomena far beyond our current understanding, perhaps even forms of organization that transcend our concepts of space, time, and physical law altogether. In this grand cosmic drama, our own universe might be seen as just one participant in an eternal dance of creation, destruction, and renewal. The principles of cosmic ecology, if they indeed operate at these unimaginable scales, could provide a framework for understanding our place in a reality far vaster and more intricate than we have ever imagined. The concept of infinity plays a profound role in discussions about the existence of multiple or endless universes, often leading to thought-provoking implications in cosmology and philosophy. When we consider the universe itself, traditional models often center around a finite space and time. However, introducing the notion of infinity expands possibilities dramatically. An infinite universe may imply that every possible configuration, event, and even every form of matter could exist somewhere within that vastness. In the context of multiple universes, often referred to as the multiverse, infinity allows for the existence of an infinite number of alternate realities or parallel universes. Some theories suggest that each decision made or event occurring could spawn a new universe, leading to an unending array of possibilities. This means that within an infinite multiverse, every conceivable outcome might exist in its own distinct universe, creating an endless tapestry of realities that could intersect with or diverge from our own. Moreover, mathematical models that incorporate infinity can suggest that the laws of physics might differ across these universes. Different constants or fundamental forces could yield entirely diverse environments, where life, space, and time behave in ways we might not even be able to comprehend. The implications of this are staggering, challenging our understanding of reality and the nature of existence itself. As scientists push the boundaries of exploratory frameworks through avenues like string theory and cosmic inflation, discussions surrounding infinity and the multiverse continue to develop. These theories aim to unify our understanding of cosmic phenomena and offer potential answers to profound questions, including the nature of reality, existence, and the very fabric of space-time. The concept of infinity thus serves as a pivotal foundation for contemplating how many universes might exist and the intriguing dynamics between them. The implications of a true multiverse for the nature of reality and existence are profound and multifaceted, fundamentally challenging our current understanding of the universe and our place within it. If a multiverse truly exists, it suggests that our observable universe is just one of countless others, each potentially governed by different physical laws, constants, and dimensions. This notion raises essential questions about the nature of existence itself, blurring the lines between what is real and what may merely be a small part of a much larger cosmic tapestry. One significant implication of the multiverse concept is that it introduces an abundance of possibilities. If every conceivable outcome occurs in some universe, this means that every choice, event, and iteration of reality potentially exists somewhere. For instance, decisions made by individuals could lead to alternate universes where different paths were taken, enhancing the philosophical exploration of free will and determinism. The diversity of experiences across infinite universes creates a richer understanding of existence, suggesting that who we are and the choices we make may have counterparts playing out in parallel realities. Furthermore, a true multiverse challenges the notion of fine-tuning in our universe. The seemingly perfect conditions for life as we know it could be explained by the existence of numerous universes, each with varying conditions, many of which would be inhospitable to life. Our universe could simply be one where the parameters happen to align favorably, ushering profound questions about the uniqueness of our own reality. This leads us to contemplate whether life itself is more common or rare across the vast multiverse, altering our perspective on existence and the likelihood of other intelligent civilizations. Lastly, the idea of a multiverse invites deeper philosophical and metaphysical discussions about the nature of reality. It challenges the conventional boundaries of physical science by positioning itself at the intersection of science, philosophy, and spirituality. If multiple universes exist, It opens avenues for considering existence as a more complex and diverse phenomenon than previously thought, further encouraging exploration of what it means to be alive and aware in a universe that may be but one of an infinite array of realities. The multiverse concept profoundly challenges our understanding of uniqueness and identity, primarily by proposing that every possibility may exist across countless parallel realities. This leads to intriguing questions about what it means to be unique in a cosmos where countless versions of ourselves and various outcomes coexist. If our choices and circumstances can create branches into separate universes, the very notion of a singular identity becomes more fluid and complex. One of the most striking implications of the multiverse is the idea that there might be infinite versions of each individual, each living out different experiences based on alternative decisions or circumstances. For example, every choice we make could potentially create a new universe where a different choice was selected, leading to entirely separate life paths. Thus, the concept of identity, which we often perceive as singular and fixed, is instead represented by a vast mosaic of possibilities, where every version of ourselves embodies different aspects of identity shaped by various life experiences. This ultimately raises philosophical questions about the nature of self. If an individual is merely one variant among countless others, what does it mean to truly know oneself? The essence of identity might be better understood as a tapestry woven from multiple threads, taking into account the myriad experiences and choices available in other universes. This invites deeper contemplation about the interplay between individual actions and the larger fabric of reality, suggesting that identity could be more collectively shared across universes rather than solely confined to personal experience. Furthermore, the multiverse concept also challenges traditional ideas of uniqueness in more general terms. If entire civilizations, events, and realities exist simultaneously, the uniqueness of specific achievements, cultures, or histories may diminish in significance within the broader multiverse context. Each creation or discovery may be replicated in other realms, prompting us to re-evaluate the value we place on individual accomplishments within a universe filled with infinite variations. Thus, the multiverse encourages a re-evaluation of both personal identity and the collective human experience, proposing that within an infinite framework, the meanings we attach to uniqueness may be far more complex than previously understood. The existence of potentially infinite copies of ourselves in other universes carries significant philosophical implications, particularly in the realms of identity, consciousness, and morality. One of the foremost questions raised by this concept is the nature of the self. If there are countless versions of an individual existing in parallel realities, it prompts deep inquiry into what constitutes personal identity. Is the essence of who we are tied solely to our unique experiences and memories, or does it extend to the myriad variations of ourselves that could exist elsewhere? This challenges the notion of a singular fixed self and suggests that identity may be more fluid and multifaceted than traditionally perceived. Consciousness is another area profoundly impacted by the concept of infinite copies. If each version of ourselves in alternate universes leads a life with distinct experiences, the question arises, what does it mean to be conscious? Does consciousness remain unique to our specific reality, or could it manifest similarly in various forms across other universes? This exploration can lead to discussions about the nature of free will, as the existence of multiple versions may suggest that many paths are not only possible, but indeed played out in parallel realities. The implications of making choices thus become more intricate, as they could lead to diverging destinies in infinite ways. Moreover, the ethical considerations of a multiverse filled with copies of ourselves can be quite complex. If every action leads to different outcomes in separate universes, does this affect our sense of responsibility for our decisions? Philosophically, this raises questions about the ethical weight of our choices. Were we to consider ourselves in a multiversal context, we might acknowledge not just the consequences of our actions in our specific universe, but how they resonate across infinite others. This could either lead to a heightened sense of personal accountability or to existential paralysis. an uncertainty about the impact of any single decision amidst countless iterations. Finally, the existence of infinite copies also invites reflection on the universality of human values and experiences. If versions of ourselves exist that live lives of varying moral character, it challenges the idea of a singular moral framework applicable to all. This can provoke thought regarding what it means to live a good life and how moral principles might shift from one universe to another. As a result, the complexities of having infinite copies of ourselves compel us to critically examine the fundamental concepts of identity, consciousness, morality, and free will within the broader context of existence. The multiverse idea introduces intriguing nuances to the long-standing debate between determinism and free will, challenging traditional notions and framing the conversation within a broader context. Determinism posits that every event, including human actions and decisions, is the result of preceding events governed by the laws of nature. In a deterministic universe, this might imply that the future is already laid out based on these influences, leaving little room for free will. Incorporating the multiverse concept, where every possible outcome of decisions exists in various realities, offers a way to reconcile free will within a deterministic framework. Each decision made by an individual could lead to the creation of an alternate universe for each possible scenario. For example, if someone chooses between two career paths, their choice creates one universe where they pursue one path and another universe where they take the other. In this sense, the multiverse accommodates both aspects. The individual exercises free will in making choices while simultaneously contributing to multiple deterministic outcomes across various realities. Moreover, the existence of a multiverse raises questions about the nature of causation and choice. If one subscribes to a deterministic view, the question then becomes what determines the choices made in each universe. Is there an underlying randomness, or are there additional factors at play influencing decisions in each reality? This dilemma complicates our understanding of personal agency and accountability. If every decision results in infinite paths, then what does it mean to say that an individual has made a choice? The individual might create numerous versions of themselves across different realities, each reflecting different choices. Consequently, the multiverse idea could suggest a more nuanced view of free will. Rather than strictly opposing determinism, it could imply that individuals navigate a complex landscape where their choices influence not just their own lives, but also give rise to numerous variations of existence. Each choice not only shapes their immediate reality, but also contributes to a richer tapestry of possibilities within the multiverse. This interplay invites a discussion of the complex relationships between identity, decision-making, and the philosophical implications for how we perceive our actions in a reality teeming with infinite potential outcomes. The implications of the multiverse for the concept of creation or a creator are profound and multifaceted, prompting deep philosophical and theological reflection. Traditional narratives about creation often center on the idea of a singular universe being intentionally brought into existence by a creator. In a multiverse framework, where countless universes may arise from various mechanisms, the nature of creation becomes drastically more complex and may challenge conventional beliefs about divinity. One possible implication is that if many universes exist, each with different laws of physics and conditions, it raises questions about the role of a creator in this grand scheme. Is a creator responsible for initiating a single universe, or do they preside over a broader multiverse? If the multiverse emerged from natural processes, such as quantum fluctuations or cosmic inflation, this could suggest that the creator's role, if any, may be more about setting the initial conditions for an entire collection of universes rather than a singular act of creation. Such a view might frame the creator not as a hands-on architect, but rather as a facilitator of natural laws that allow multiple realities to unfold. Moreover, the existence of infinite universes with varying characteristics might imply a more nuanced understanding of divine purpose. In a multiverse narrative, It is conceivable that the diverse environments and potential forms of life across these universes could reflect a creator's intent for exploration and variety, fostering a richer expression of existence. This perspective could invite interpretations where individuality and freedom within each universe are seen as reflections of a creator's diversity of expression. On the other hand, the multiverse concept may also challenge theological perspectives that posit a personal, interventionist deity who closely interacts with creation. If universes can arise spontaneously through physical processes, questions emerge about the necessity of a creator in the traditional sense. This leads to potential philosophical implications regarding purpose and meaning. If we are simply one of many possible realities, what significance do our actions and existence hold within the broader multiverse context? It may prompt a shift in how we pursue understanding purpose beyond the constraints of a single universe. Ultimately, the multiverse concept invites various interpretations of creation, prompting enriching discussions around the nature of divinity and existence. It encourages a re-evaluation of spiritual beliefs and our understanding of reality, highlighting the potential for diverse and evolving narratives that intersect at the complex junction of science, philosophy, and personal belief. The existence of multiple universes has the potential to significantly alter our understanding of cosmic evolution and complexity. If a multiverse exists, it suggests that our own universe is just one of many, each evolving under different conditions and governed by varying laws of physics. This notion opens up fascinating avenues of inquiry regarding how complexity arises, not only in our universe but across all potential universes. One of the most striking implications is the idea that the properties and constants governing our universe might be specifically tuned for the emergence of complex structures such as galaxies, stars, and life. In a multiverse scenario, however, each universe could have different physical constants which might result in drastically different evolutionary pathways. Some universes may evolve into regions teeming with life, while others might remain barren and uninhabitable. This variability suggests that complexity is not a universal outcome, but rather one of many possibilities, contingent on specific conditions. Furthermore, exploring cosmic evolution within a multiverse context allows for a broader understanding of processes such as cosmic inflation, dark energy, and the formation of structures. For instance, if inflation can occur in multiple universe scenarios, it provides an explanation for how different regions of space can evolve independently, each giving rise to unique cosmic histories. This could account for phenomena like the vast variation in galaxy formation and development throughout the observable universe, as our universe is just one realization of cosmic evolution among an infinite tapestry of others. Additionally, the multiverse framework may invite reconsideration of the principles of natural selection and emergence. In a context where numerous universes exist, we can formulate hypotheses about how complexity might arise not solely from adaptation to specific environments, but also from entirely different evolutionary pressures in parallel realities. This could illuminate the dynamics of design, organization, and complexity over a much wider field of possible realities, encouraging scientists to explore new theoretical models that account for those variations. Ultimately, the existence of multiple universes could enrich our understanding of cosmic evolution on a grand scale. By examining the interplay of different laws of physics and initial conditions across numerous realities, we can gain deeper insights into the emergence of complexity and the rich diversity of existence, encouraging a rethinking of not only the mechanisms behind cosmic formation, but also our place within the vast cosmos. The ethical implications of decisions and their consequences in a multiverse scenario are complex and thought-provoking, fundamentally altering how we might view responsibility, morality, and the meaning of our choices. In a reality where every possible decision creates a branching universe with its unique outcomes, the understanding of ethical accountability becomes multifaceted. In traditional frameworks, moral responsibility is often linked to the consequences of specific actions. If one takes a certain action that leads to a negative outcome, they are held accountable for that decision. However, in a multiverse, an individual's decision could imply infinite variations where different consequences unfold in parallel realities. This raises significant questions about the ethics of decision-making. For instance, if a person chooses to act in a way that leads to harm in one universe, it might also result in positive outcomes in others. Does this mean that their moral responsibility is diluted or diffused across multiple realities? Such a scenario challenges the idea that individuals are solely accountable for their actions, suggesting a more collective understanding of morality that spans multiple existences. Furthermore, individuals may grapple with a sense of existential paralysis in a multiverse, questioning whether their choices truly matter if every possible alternative is realized. This could lead to feelings of ambiguity about the significance of ethical decision-making. If one feels that their actions will be replicated in countless other universes, they may question the impact of their moral choices, potentially leading to ethical nihilism or a sense that it is futile to strive for good. Conversely, this awareness might also inspire a broader sense of compassion and connectedness, recognizing that actions resonate not just within a single thread of existence, but across an interconnected web of realities. The multiverse dilemma also engages discussions around the concept of empathy. If we accept that counterparts of ourselves experience a myriad of outcomes based on our shared decisions, it may compel us to cultivate a deeper sense of empathy towards others. Understanding that each decision carries weight across different realities prompts individuals to consider the implications of their choices in a more expansive context, potentially fostering a desire to make ethical decisions that contribute positively to the collective experience of sentient beings across multiple universes. Ultimately, the ethical implications of a multiverse scenario confront us with fundamental questions about responsibility, the significance of choice, and the interconnectedness of existence. Engaging with these concepts not only encourages deeper reflection on our moral frameworks, but also challenges us to navigate the complexities of ethics in a reality that may encompass infinite possibilities and outcomes. The multiverse concept significantly challenges our traditional notions of causality and effect, reshaping how we understand cause and effect relationships in a complex universe. In classical physics, causality is typically viewed as a linear progression where a specific cause leads to a specific effect. This sequential nature of time and space ensures that every event is the direct result of preceding events, providing a straightforward framework for understanding the relationships between actions and their outcomes. However, in a multiverse scenario where every possible outcome of any decision or event exists in parallel realities, the linear connection of causation becomes more intricate. Each choice or event can give rise to multiple universes, each experiencing different consequences. This suggests that causality might not be a singular unidirectional flow, but rather a branching tree, where numerous effects emerge from a single cause. Each branch represents a different timeline or reality that unfolds based on various possibilities, complicating our understanding of how causality operates at a fundamental level. Moreover, the existence of multiple outcomes in different universes raises questions about the nature of causative relationships. If every potential scenario occurs, what does it mean for effect to follow cause? For instance, if a person makes a decision that leads to both successful and unsuccessful outcomes in different universes, how do we attribute effect to a single cause? This complexity challenges the traditional view that one can reliably predict outcomes based on specific actions, as the same action might yield wildly different results in parallel realities. Additionally, the concept of causality becomes intertwined with the ideas of chance and randomness. In a multiverse, events can appear to be determined by random fluctuations, leading to varying outcomes across different versions of reality. This brings forth philosophical questions concerning determinism, free will, and the role of chance in the evolution of universes. It raises the possibility that what we perceive as random could be a mere reflection of the infinite variety within the multiverse, where each outcome is valid in its own context. Ultimately, the multiverse concept compels a re-evaluation of our understanding of causality and effect, pushing us to consider more complex interactions and the implications of choices that resonate across multiple realities. This expanded perspective emphasizes the intricate web of possibilities that define our universe and encourages a deeper inquiry into how actions, decisions, and events shape not only our immediate experiences, but also the broader tapestry of existence across infinite realms. The multiverse concept carries profound implications for the notions of cosmic significance and purpose, prompting a re-evaluation of what it means to find meaning in a universe or series of universes where countless realities coexist. Traditionally, many philosophical and religious frameworks assert that our universe is unique and purposeful, often linking human existence to a grand design or overarching narrative. However, the existence of the multiverse suggests a vastly different perspective on significance and purpose. If our universe is just one of innumerable others, each with varying laws of physics and distinct histories, the idea of a singular purpose becomes more complex and potentially diluted. In a multiverse, the events and achievements of our universe may seem less unique when viewed alongside countless other realities where similar or even differing events have unfolded. This raises essential questions about the uniqueness of human experience and cosmic events. Does this imply that our endeavors, struggles, and achievements are less meaningful because they are replicated in other universes? Alternatively, one could argue that purpose is amplified through the sheer diversity of existence, fostering rich narratives across all realities. Additionally, the multiverse perspective invites exploration into the nature of meaning itself. If every possible outcome occurs, it suggests that significance might not be confined to a single trajectory. Instead, it could be viewed as a broader tapestry of existence, where each universe contributes uniquely to the grand narrative of the multiverse. This perspective encourages a more inclusive understanding of cosmic significance, one where meaning is derived not only from our individual experiences, but also from the multitude of narratives woven throughout countless realities. Furthermore, the multiverse concept can lead to a more flexible view of purpose that aligns with individual experiences and choices. In a reality where endless possibilities exist, individuals may find personal meaning in their unique circumstances, decisions, and interactions within their specific universe. This offers an empowering notion that purpose can be self-defined rather than dictated by an external framework. Individuals might seek to create their own significance through their actions and relationships, contributing to the vast diversity of experiences in the multiversal landscape. Ultimately, the multiverse invites us to critically reflect on the concepts of cosmic significance and purpose, challenging us to explore meaning in a broader context. It encourages a view that embraces the interconnectedness of existence across infinite realities, while allowing for personal interpretations of significance grounded in individual agency and experience. This complex interplay of universes opens rich avenues for philosophical inquiry, fostering discussions about what it means to find purpose in a reality teeming with limitless possibilities. The concept of a living cosmos suggests that the universe or multiverse exhibits traits reminiscent of living systems. This doesn't imply consciousness as we understand it, but rather complex, self-organizing behaviors and the capacity to evolve. In realms beyond our observable universe, entire universes might function like cells in a vast cosmic organism, each playing a crucial role in maintaining a larger structure. These universes could exchange information or energy through quantum entanglement or higher dimensional connections, forming a cosmic neural network. This interconnectedness might allow for the propagation of cosmic signals across the multiverse, influencing the development and behavior of individual universes in ways we can scarcely imagine. Universes might reproduce or spawn new universes through processes analogous to cellular division. A universe could reach a critical point of expansion or energy density, causing it to split into separate universes, each inheriting characteristics from its parent but developing unique properties. This cosmic mitosis might be triggered by specific conditions, such as the density of dark energy reaching a critical threshold or the formation of specialized structures within the universe. Alternatively, black holes in our universe might serve as seeds for new universes, with matter collapsing into singularities that punch through space-time, emerging as big bangs in new realms. This process could create a nested hierarchy of universes, each containing the potential for infinite new creations within its own structure. Cosmic natural selection proposes that universes with certain properties are more likely to produce offspring universes. Universes that can form stable black holes or achieve specific energy states might be more prolific in spawning new universes. This process could lead to a multiverse populated by universes with increasingly stable and complex properties, analogous to biological evolution. Over cosmic timescales, this might result in the emergence of universes fine-tuned for the creation of complex structures or even life. The process of cosmic natural selection could also explain the apparent fine-tuning of our own universe, suggesting that our physical laws are the result of countless iterations and refinements across generations of universe creation. Universes might evolve over time through interactions with other universes or by adapting to internal changes. The laws of physics themselves could be subject to mutation and selection, with universes that develop stable, life-supporting laws being more likely to persist and reproduce. This evolution might be driven by the accumulation of information or complexity over time, leading to increasingly sophisticated universal structures. As universes age, they might develop new properties or capabilities, such as the ability to support more complex forms of matter or energy. This cosmic evolution could also involve periods of rapid change, analogous to evolutionary punctuated equilibrium, where new universal forms emerge in response to changing conditions in the broader multiverse. The concept of universe metabolism suggests that universes could exchange energy or information, maintaining a cosmic equilibrium. This exchange might occur through higher dimensional connections, quantum entanglement across universal boundaries, or through the creation and absorption of baby universes. Some universes might specialize in energy production, while others focus on information processing, creating a diverse cosmic ecosystem. This metabolic process could involve the transfer of fundamental particles, fields, or even abstract quantities like information or entropy. In this cosmic economy, the waste products of one universe might serve as vital resources for another, creating intricate webs of interdependence across the multiverse. Symbiosis between universes could manifest in various intriguing ways. Universes might develop mutually beneficial relationships, where the output or waste product of one universe serves as essential input for another. For example, the entropy or information loss in one universe could fuel the creation or complexity in another, creating a balanced cosmic cycle. Some universes might act as cosmic incubators, providing ideal conditions for the formation and growth of baby universes. Others might serve as stabilizers, helping to maintain the overall structure of the multiverse. This cosmic symbiosis could lead to the emergence of universe clusters or superorganisms composed of multiple interconnected universes, each playing a specialized role in the larger entity. The idea of cosmic immune systems proposes that universes might develop mechanisms to protect themselves from collapse or intrusion. This could involve self-regulating processes that maintain stable physical constants or barriers that prevent harmful interactions with other universes. Universes that develop robust immune systems would be more likely to survive and reproduce in the larger multiverse. These protective mechanisms might include the ability to repair tears in space-time, neutralize potentially destructive fluctuations in vacuum energy, or even repel invasive forms of matter or energy from other universes. Over time, universes might evolve increasingly sophisticated defense mechanisms, leading to a kind of cosmic arms race between different universal forms. In a multiverse scenario, different types of universes might occupy various ecological niches. Some universes could specialize in producing complex structures, while others might excel at energy production or information processing. This cosmic differentiation could lead to a rich tapestry of universal types, each adapted to specific roles or environments within the larger multiverse structure. For instance, Some universes might be optimized for the production of black holes, serving as cosmic engines that drive the creation of new universes. Others might specialize in supporting diverse forms of life, acting as cosmic biodiversity hotspots. The interaction between these specialized universes could drive the overall evolution and complexity of the multiverse. Cosmic biodiversity in a multiverse could be crucial for the overall stability and evolution of the cosmic ecosystem. A diverse range of universe types, each with unique properties and capabilities, could make the multiverse more resilient to large-scale disturbances or changes. This diversity might also drive innovation and complexity at the cosmic scale, as different universe types interact and influence each other. Just as biodiversity on Earth contributes to the resilience and adaptability of ecosystems, cosmic biodiversity could ensure the long-term survival and evolution of the multiverse as a whole. This diversity might manifest in countless ways, from universes with different numbers of dimensions to those operating under entirely alien physical laws. The principles of adaptation and fitness could apply to universes in a larger cosmic ecosystem through a process of selection and reproduction. Universes that are better fit, perhaps those that can sustain complexity, produce black holes, or maintain stable physical laws, might be more likely to spawn new universes or persist over longer cosmic timescales. This cosmic fitness landscape could drive the evolution of universes towards increasingly stable and complex forms. The concept of fitness at a universal scale might involve factors we can barely conceive, such as a universe's ability to support the emergence of consciousness, its capacity to store and process information, or its resilience in the face of cosmic catastrophes. As universes compete and adapt within this vast cosmic arena, the multiverse itself might evolve towards greater levels of complexity and order.